You know, of all the amazing things about the universe, I think two stand above all the rest. One of them is that we know so much about the universe, but another is that there's even more that we don't know. And what I want to focus on for this lecture is the inexplicable universe from a time gone by that is now explained. Human cultures have for a long time harbored scientific mysteries. In fact, in the pre-scientific era, that would be before Galileo, 400 years ago, before then, many of nature's most unknown mysteries were thought to be the work of divinity. Take, for example, epilepsy. There's someone writhing on the ground, your best friend, frothing at the mouth. If you're driven by Christian theology, your first thought is the person is possessed by the devil. That's the natural explanation for what's going on there, in the absence of any other knowledge about neurosynaptic processes. In another example, you could go out to the woods one morning, one damp, cool morning, and you'll find this circle of mushrooms. No one knew how they got there. You were there the day before, there was no trace of mushrooms. And now there's a perfect circle of them. These were known as fairy circles. And people imagined sort of woodland nymphs, woodland fairies coming to have a jamboree, and these were their chairs. Little fairies, of course. These were their chairs where they celebrated whatever were their rituals of the night. We would later learn that, of course, mushrooms they're not solo organic entities. They're, in fact, one spore can generate many, many mushrooms. And if a spore drops in one spot, it can work its way out and get ready for just when the conditions are right, just the right temperature, just the right humidity. And then they all pop up, equidistant from where that spore first dropped. So explanations came later to these phenomena. And of course, we know epilepsy is the result of random firing of the brain, uncontrolled firing, that leaves you helpless in the presence of a brain gone awry. So what we found is that things started to change in the rise of the experiment. If you go back in time to Aristotle's day, people imagined that you could just sit in a chair and just think about the universe. You didn't have to go out and test it. You just thought it up. Aristotle imagined that heavy things fell faster than light things. Of course, yes, a rock falls faster than a feather. The feather feels the air resistance on its way down. But take a heavy rock and a light rock, they'll actually fall together at the same rate. Aristotle, however, said that the heavy one will fall faster than the light one in direct proportion to its weight. This is patently false. And it would take Galileo 1,500 years later to demonstrate that this was the case. He describes the experiment of dropping two balls from the side of the Leaning Tower of Pisa. And they're both falling at exactly the same rate, hitting the ground at the same time. Of course, that would happen with a rock and a feather. You just have to evacuate the air from where you're doing the experiment. In fact, that was indeed done, that very experiment, on the surface of the moon. So what I want to do for this lecture is focus on several stunning examples of profound mysteries that plagued the deepest thinkers of their day, but ultimately got explained. There was a single biggest scientific mystery of the 19th century. It preoccupied the greatest minds of that period, and what it related to was at the core of our understanding of space itself. What's behind it? Well, we know that waves require some kind of material medium through which to travel. And the best and most common example of a wave is sound. Sound moves through air, but if you take away the air, it cannot propagate. You may have remembered this experiment. It might have happened in your high school science class. You have a ringing bell. and you enclose that bell in a glass container, and you start pumping the air out of that glass container, and the ringing bell gets dimmer and dimmer and dimmer to hear. And at some point, you don't hear it at all, yet you still see it clanging away. That's evidence that sound cannot pass through the vacuum that you just created. Well, if light is a wave, then it too must require some kind of medium through which to travel. Here's the problem. Empty space is a vacuum, and we know that light reaches us from empty space. The moon is in space, the sun is in space, the stars are out in space, and there's a vacuum between us. So it was hypothesized that no, there's not air out there. There's got to be something, some substance, some medium that light requires for it to propagate. And we gave it a name. My science ancestors of that period, we gave it a name. It was called the ether. The ether. We ought to be able to measure it. Two scientists came along. This is in the late 1800s. The physicist Albert Michelson and the chemist Edward Morley. Two American scientists. And they got together, collaborated, and perfected a new kind of tool called the interferometer. It's a special instrument that allows you to measure with high precision distances and speeds. And so in 1897, they conducted what came to be known as the Michelson-Morley experiment. So here's what they did. They said, all right, here's Earth. I'm going to measure the speed of light with the movement of Earth around the sun. Then I'm going to measure the speed of light against the movement of Earth around the sun. And if there is an ether out there, I ought to be able to show that the light added to Earth's movement, and I measure the speed of that, I'll get the speed of light plus the speed of the Earth. And coming back the other way, if I make that measurement, I'll get the speed of light minus the speed of the Earth. That makes complete sense. Of course it does. If you're riding in a train, back then it would have been a train, not a car, you're riding in a train that's going 30 miles an hour and you send something forward 10 miles an hour, you add them, that object is moving 30 plus 10, 40 miles an hour relative to the ground. Come back the other way and you throw it out the back end of the train, that speed will be 30 minus 10, 20 miles an hour relative to the ground. It's that simple. That's all they were trying to do with the speed of light. Upon conducting this experiment, what they found is that the speed of light was the same no matter where they made the measurement. And this was astonishing. It was the greatest null result ever found for a scientific experiment. A null result is you expect to find some kind of measurement and you don't. Usually those experiments are like not interesting, but this was the most interesting null experiment ever conducted. And so what do? Everyone knew there had to be an ether. So there were a couple of guys who said, all right, we can solve this. There's a fellow named Lorentz and another one named Fitzgerald. And they got together and said, we know what's going on because there's got to be an ether. Your measuring tools have contracted in the direction of motion. They've physically contracted to fool you into thinking that you're getting the same speed of light. That must be going on. Now, just think about that. So embedded were they in the existence of the ether. The ether, this traditional concept that a wave requires a medium, that they would not even entertain the possibility that there was no such thing as an ether. They would rather assert that something odd was happening to your measuring devices. They were trying to rescue the hypothesis of the stationary ether. Now, we happen to know that physical materials can't just physically contract. That's not how they behave. They never behave that way. What we would later learn, not just a few years later, is that light, in fact, does not need a medium after all through which to propagate. It is a self-driven wave, a combination of an electrical wave and a magnetic wave. It was an astonishing revelation of the day. No ether. And what state of mind, though, allows us to recognize that the speed of light remains constant? Albert Einstein to the rescue. 1905, special theory of relativity. What he noticed was that those equations that would shrink your physical objects that are doing the measurements to conspire to give you the same speed of light, what Einstein showed is, no, they don't actually shrink. What happens is the speed of light is actually constant. It's actually constant. And what's going on is that the rules of special relativity change how you end up making that measurement while you're doing it. And when that comes about, you find that the ether is not necessary, the speed of light is constant, and we have walked through a proscenium in the history of science where the ether was the last grasp, the last bastion of classical physics before the 20th century would open its doors. Because in the 20th century, what we came to learn is that whatever was your common sense that you were invoking about how the world must be, 20th century science and onward entered a time where, in fact, in order to understand the universe, at least some of the time, you had to abandon your senses. Next up is the discovery of the planet Neptune. But first, let's go back in time to 1781 for the discovery of the planet Uranus by Sir William Herschel. He's the only one in town with the big telescopes during that day. And he found Uranus by accident, actually. He thought he had found a comet. Nothing else sort of moved against the background stars except comets. It was inconceivable to him that he could have discovered a planet because nobody had ever discovered a planet before. Mercury, Venus, Mars, Jupiter, and Saturn in the sky are visible to anyone who looks up. They don't require a telescope. He was in denial for so long. He thought he had seen a comet, and he would say things like, "Curious comet this is. It refuses to show any fuzz, as any good comet ought to." Fact is, the man discovered Uranus. So here's the question. Does Newton's law of gravity apply that far out in the solar system? Newton's laws of gravity had been tested between the Earth and the Moon and all the inner planets and the Sun, and it was working. It was good. It was powerful. It was predictive. And so here we are at the outer reaches of the solar system. Well, let's test that. We're in the era of testing ideas. So let's wait 70 years. And over those 70 years, we're going to get data on where Uranus is in its orbit. Okay? How long does it take Uranus to complete an orbit? 84 years. So 70 years is most of 84. So you're doing good. You've got a lot of good data to compare. You say, where should Uranus be according to Newton's laws? And where do I measure it to be in the solar system? Is there a difference or not? If it's bang on, we're good. Newton's laws work out there, we're fine. What we found is that they didn't match. Do we throw out Newton's laws? You know, they're pretty good. They're working for us. No one really wanted to abandon them. If you don't abandon them, what are your options? Maybe there's another source of gravity you haven't reconciled with your efforts. All the other sources of gravity you factored in, you're missing one. And if you included it, maybe that would account for why it looks like Uranus is behaving badly. So, thus began the hunt. British mathematician and astronomer John Couch Adams, he was a specialist in celestial mechanics. This is the physics and the mathematics of the movement of bodies in the solar system. And a French mathematician, Urbain Jean-Joseph Leverrier, did exactly the same thing. And it's a tricky problem because typically you would use Newton's laws by saying, here's a body and here's a body, calculate the force between them. This is different. Here we have the force between them, but there's some body out there and we don't know where it is or how much mass it has. So it's an inversion problem with Newton's laws. You have to calculate things backwards from what you're accustomed to, and that takes pages and pages of data and calculations to get it right. So each of these brilliant mathematicians predict where and when you should find the perturbing object that was out there. It happened to be Leverrier, who was friends with Johann Gottfried Galle in the Berlin Observatory. He was an astronomer there. Leverrier assisted him, told him, here's where you should look, and here's when you should look. Johann Galle looked where and when Leverrier said he should find it. Within 1 degree of the predicted position, he found a new planet. The planet to be known as Neptune. This was a triumph of mathematics and the laws of physics. It was a case where you weren't using the past history of rhythms to predict the next event. You do that with like the phases of the moon and eclipses and things where you have a good record of what it was doing before. This was a case where there was no previous record. A planet was predicted and discovered simply by laws of physics and understanding the operations of nature. This would shape the expectations of all subsequent discoveries in the solar system because Newton's laws were working. And next, we would apply those very same laws to the orbit of Mercury. Nature can be subtle. I don't know if that's a good thing or a bad thing just yet, but it's certainly true. I'll give you some examples. Take Newton's laws. Newton's laws of motion and gravity are powerful tools that enable us to understand and decode the movement of objects in the solar system. And it's worked in every place we'd ever applied it. So why not be cocky about it and say it'll work even in places we have yet to imagine? These methods and tools are empowering our capacity to understand objects in the solar system. Okay, I'm with you on that. That Newton's laws, they're good. They're good. But let's see what happened. Over the centuries, careful timing of the movement of Mercury around the sun, that's the innermost planet. It orbits in an ellipse. It turns out the ellipse precesses around the sun. We've known this. This is not news, right? While Mercury is orbiting, the entire ellipse precesses ever so slightly. All right, we're fine. Turns out, when you calculate how quickly this should precess, and then you observe how fast it's precessing, those two numbers do not match. They differ from each other by, if you're angle fluent, 43 arc seconds per century. That's small, and it took a long time to establish that baseline of measurement to say that these two do not agree. All right, well, what's causing it? Nobody knew. But in 1859, riding high on his successes with the planet Neptune, Leverrier said, I got this. Look, I've been there before. How do you think I helped you find Neptune out there? There must be some other source of gravity we've yet to tally in our inventory of objects in the inner solar system. So he said, I got it. Maybe there's a belt of asteroids, a second asteroid belt in the solar system between Mercury and the sun. And the collective gravity, that's what's giving an extra tug on Mercury. Within a few years of that, there was an astronomer who made a measurement of a planet moving across the sun's surface, a planet that was not Mercury. Leverrier said, okay, I don't need the asteroid belt. It must be that object. In fact, I'll name it. I'll call it Vulcan. Awesome name for a planet. Anything that close to the sun, that's the name it has to have. That's the root of the word volcano. So that became the scapegoat for this extra tugging on Mercury to create that difference in the precession. Problem is, another person with a better telescope observing the sun at the same time as this other astronomer was making his measurements said, "I saw nothing go across the sun. There must be something wrong with your measurements." And practically overnight, Vulcan disappeared from the data. It was a faulty measurement that had been reported. So now Leverrier was left with nothing to credit for the movement of Mercury. But maybe you can still get away with it. Maybe it's so close to the sun, it's always lost in the glare. Plenty of people were happy with that explanation. And we went on saying, yep, it's Vulcan. Never found it. We don't know where it is, but surely it's there. Enter Albert Einstein. 1916. He publishes the general theory of relativity, the modern theory of gravity. In it, space and time is a fabric. Think of it as a deformable fabric. And gravity is not a force between two objects. Gravity is the shape of that fabric. And bodies move according to where that shape tells you to go. And when you factor in all the tenets of relativity, what we found is that Mercury was following the severely curved fabric of space and time in the vicinity of the extremely significant and strong source of gravity that is the sun. In fact, Newton's laws do fail when you're that close to an extreme source of gravity. This shocked the world. And it's a reminder that here we were invoking Newton's laws. We were ready. We invoked Newton's laws to discover the planet Uranus. And in our cocky ways, we said, we're going to fix the Mercury problem the same way. Only to find out, no. Mercury required an entire new branch of physics to be invented, just to explain it. And so, yes, nature can be subtle. That is the beauty and the challenge that the modern scientist faces. You know, not all investigations of the universe involve pieces of the unknown. Occasionally, people are challenged to take it all in and come up with a coherent, complete understanding of the known universe. In fact, the people who get to do this are part of cultures that value deep thought, that actually have the luxury of time to invest in trying to deduce the nature of the known world. One of my favorite examples of this is Claudius Ptolemy. He was an Alexandrian astronomer and mathematician, and he was around at 2nd century AD. He came up with a coherent, complete understanding of the known universe. And he put it all in a book called Almagest. Almagest is actually Arabic for the greatest. Aptly named, I think. Now, his ideas happen to be wrong. He put the Earth in the middle of the known universe. That's the geocentric model of the cosmos. But when you think about it, that's what the world looks like. Everything orbits Earth. And does it feel like Earth is moving under your feet? No. So his model was what made common sense to everybody. But deep down inside, I think he was still didn't feel like he grasped it all. Because he would follow the movements of the planets in the night sky. They would slow down, stop, and then reverse, call that retrograde. This is complicated motion to try to explain. In his greatest work, he penned in the margin my favorite quote of all time. He said, "When I trace at my pleasure the windings to and fro of the heavenly bodies, I no longer touch earth with my feet. I stand in the presence of Zeus himself and take my fill of ambrosia." That's Claudius Ptolemy basking in what he understood about the universe, but was humble in his ignorance. Because deep in that quote was the recognition that I don't think he really believed he fully understood what was going on. Why else would he bask in the presence of Zeus? Well, it would be 1,400 years where people just accepted the geocentric model. Again, that's an era where experiments on ideas is not yet an understood thing to do. 1,400 years would go by. Nicholas Copernicus, 1543, on his deathbed, would propose the heliocentric model of the universe. He wasn't content with what the hoops Ptolemy had to jump through to account for what we saw. How else do you get planets to go forward and backwards and forward and backwards? Ptolemy had systems of multiple orbits on top of orbits called epicycles. Things orbiting nothing in space. In fact, the word orbit wasn't even quite defined back then. This was just movements. And Copernicus said there might be an easier way. Let's put the sun in the middle of the known universe, and if you do that, Earth becomes one of the planets. That's heretical. Copernicus waited to his deathbed before he published this, knowing the kind of retribution that would be exacted upon him in that period of Europe, the mid-16th century. Did not take kindly to heretics. So you can't kill him, he's already dead. So he puts out the heliocentric universe on his deathbed. It was right in every fundamental way, except he had the orbits as perfect circles. It would take a few years to iron that out. But what's important here is that the world embraced an idea that was wrong, but made sense. Wrong, but it made sense. That ought to tell us something. That not everything in the world that makes sense is correct. And if that's the case, then who are you? What of Ptolemy's Zeus? What of the reverence he's showing? If he actually understood it all, would Zeus have even shown up in his quote? And if you're prone to assert that God is the influence of all that we don't understand, because the hand of God is greater than anything your mind can comprehend, then what of God? Throughout history, the urge has been strong to, upon recognizing your area of ignorance in the universe, to assign the handiwork of God to those ideas, to those phenomena. If you feel that way about prevailing ignorance, then you're actually in pretty good company. Isaac Newton did just that in his most famous work, Principia Mathematica. The translation from the Latin is The Mathematical Principles of Natural Philosophy. That's the full-up title of that book, published in 1687, in which he discovered the laws of motion, the universal law of gravitation, and in it, it represents the fruits of his effort for having discovered calculus to solve some of the problems that he engaged in. All right, so in this great work, he tries to understand the solar system as a total collection of objects. And he applies his universal law of gravitation. It calculates two bodies at a time, Earth and the Sun, Earth and the Moon, Earth and Mars. When you do this, the calculations come out just fine. But of course, the solar system is the sum of all the tugs that go on with all the planets. His attempt to do that with his two-body equations failed. What did his calculations show? That these multiple tugs on all the planets by all the other planets would render the solar system unstable and planets would fly out into interstellar space. Well, first of all, he knew that that wasn't happening and that his universal law of gravitation worked. So he concluded that divine providence must be at work. The hand of God is stepping in every now and then to correct things. Okay, well, a century would pass, before the publication of a great work of mathematical physics by the French mathematician Pierre-Simon Marquis de Laplace. He came out with a 5-volume tome called Céleste Mécanique, Celestial Mechanics. This is at the turn of the century from the 1700s to the 1800s. A contemporary of Napoleon, by the way, but I'll get back to that in a moment. So, in this volume, he develops a new branch of mathematics that allows you to take one major source of gravity and a lot of other little sources of gravity. It's called perturbation theory. It is the exact kind of math necessary to calculate what the entire solar system is doing all at once. When he does this, he shows that the solar system is stable, contrary to what Isaac Newton attempted to show a century earlier. Napoleon summoned up this work, read it from cover to cover. Napoleon himself, he wasn't just a tyrant general. The guy read everything he could in physics and engineering, two major branches of study that help you win wars. He also calls in Laplace and said, "Sir, you make no mention of a designer of this system." That's direct reference to Isaac Newton's crediting the hand of God for fixing things. Laplace, in reply, said, "Sir, I had no need for that hypothesis." So there's a lesson in there. The lesson is we're always surrounded by ignorance on some level or another. If you're going to assign God to that ignorance and you lose your curiosity to investigate it, solutions elude you. Isaac Newton said God did it and stopped working on the problem. Laplace, whatever he thought of God, what is certain is that he saw it as a really cool problem that needed a solution. And so, as we go forward, I look at the problems that existed in the past that got solved. I look at the problems that surround us today on the frontier of the advance of science. I imagine we'll solve most of those. Some maybe we're not smart enough as a species to get there. And then, of course, there are the problems yet to be identified because they only show up after we've learned that much more about the universe to even ask such questions. That's what excites me about the entire moving frontier of science. Today I want to talk about explained but nonetheless mind-warping facts about phenomena and objects in the universe. Some of them are actually downright spooky. And I'm going to begin with the basic constituents of matter. You know, by 1900, the very existence of the atom was still a hypothesis. Atom, you may remember, is Greek for indivisible. 1897, the electron, the very first atomic particle, was discovered by British physicist J.J. Thomson. There it is, discovered. No other particle is known. So what does he say about the electron? He says, in toasts that he would give at dinner time, he would say, "To the electron, may it never be of any use to anybody." So what is an electron? We can measure its charge. You can measure its mass. It actually has something that we call spin. And you can measure its effect on other particles. You can measure all of this. But you know something? The electron itself has never actually been observed. Not ever. In fact, the electron is smaller than anything ever measured ever. Whatever is its size, we have yet to figure out how small it is. And as far as we're concerned, it could be infinitesimally small. That's the electron, the particle that we all know and love. Then you've got the proton, discovered in 1911 by New Zealand physicist Ernest Rutherford. How did he discover it? Well, he beamed helium nuclei. So what's a helium nuclei? It's got 2 protons in it and 2 neutrons, but the neutron wasn't discovered yet. But he knew they were the nuclei of helium atoms, sometimes called alpha particles. He hammered gold real thin and suspended it in a thin gold foil curtain. And he sent helium nuclei, alpha particles, into that gold foil. And he checked to see how many of them are deflected, how many of them go straight through. And what did he find? Nearly every single helium nucleus that he sent into that gold foil passed right on through unperturbed. This is solid gold foil, what we would call solid. He would conclude that atoms are mostly empty space, a staggering amount of empty space. In fact, the volume of the atom is a quadrillion times larger than the volume of the nucleus itself. If you want a sense of that scale, take a BB, stick it in the pitcher's mound of a baseball stadium, and the size of the BB is to the stadium as the size of a nucleus is to the atom. So Rutherford, who discovered this, he is rumored the next morning after he realized that matter is mostly empty space. He is rumored to have been afraid to step out of his bed onto the floor out of concern that he might pass through the solid floor of his residence. This is the consequence of being the very first person in the world to know some truths about the nature of matter. Another particle, where we have electrons, protons, neutrons. That was discovered in 1932 by British physicist James Chadwick. Neutron. That took a little longer to discover because it has no charge. And if you have no charge, it's hard to find ways to interact with it to discover that it's there. We would later learn that the neutron and the proton, they themselves are not fundamental, but they're made up of quarks, 3 quarks each. Well, if they each have a charge, an electron is -1, a neutron is neutral, a proton is +1, and if the neutron and proton are composed of quarks, then the quarks must have fractional charge. In fact, they do. The quarks come in charges of 1/3 and 2/3. These are the charges that quarks have. And you can combine them in different ways to recover either 0 charge or the charge of +1 for the proton. Quarks were theorized in 1964 by American physicist Murray Gell-Mann and George Zweig. 4 years later, they would be discovered at the Stanford Linear Accelerator Center, 1968. 1968, the most turbulent year in American history since the Civil War. Assassinations, Tet offensives, the Vietnam War. Yet, the march to understand the universe persisted, such as the challenges of a nation. Where did this word come from? Murray Gell-Mann had been reading James Joyce, Finnegan's Wake, and he came upon a passage, 3 quarks for Muster Mark. Sure he has not got much of a bark, and sure any he has, it's all beside the mark. Knowing that 3 quarks are in your neutron and your proton, he figured, why not call them quarks? There are 3 regimes of quarks: low energy, medium energy, and high energy. The low energy ones, we call them up and down, 2 quarks, up and down. Medium energy, charmed and strange. High energy, top and bottom. The total number of quarks in this universe are 6. 6 quarks. So Murray Gell-Mann got it wrong. He thought there were only 3, but there are 6. They're still called quarks. All right. Here's what's spooky about quarks. You can never isolate one in free space. You can't. You know why? Because here's a pair of quarks that are bound together, and you're going to go try to separate them. So, all right, I challenge you to do that. So you grab one side and the other, and you start pulling and pulling and pulling. Well, quarks have a particular property that the force that brings them together gets stronger the more you pull them apart, not weaker. That's spooky unto itself. But here's what happens. You pull them together so far, you're pumping energy into it at such a level that the moment you successfully separate them, the energy you put in them spontaneously becomes another pair of quarks. So the one you pulled out here, another quark gets manufactured out of the energy you pumped in. E equals mc squared, the equivalence of mass and energy. The other quark, the energy you pumped into that, it makes a second quark. So you start it with one pair, you separate them, now you have two pairs. And at no time did you ever isolate a single quark. That's how quarks behave. They don't ever want to be lonely. That's spooky to me. Quarks. Always in pairs. Now you got another particle, the neutrino. That's a spooky one, the neutrino. That was predicted in 1930. It would take 26 years to discover it. Why? Because the neutrino hardly interacts with anything. It comes out of a nuclear reaction and the particle just escapes. It is fast-moving, it is ghost-like, it's made in abundance in the sun's core. And it's made in even higher quantities when a star dies in an explosion, a supernova explosion. Now, the neutrino hardly ever interacts with matter, and I'll give you a quantitative measure of that. If you take an entire light year of lead, a light year of lead, that's 5.8 trillion miles of lead spread out through space. Go ahead, get that. And send a neutrino through one end. You might block the path by the time your light year of lead has been traversed. That's how unsociable neutrinos are. And because of how many are made in the center of the sun, you can calculate how many these are. 65 billion neutrinos pass through every square centimeter of your skin every second. All from the sun. Neutrinos, ghost-like particles, no charge, traveling nearly the speed of light. So these particles we don't experience them in everyday lives. They reveal themselves to us in particle accelerators. So you can say, oh, that doesn't make sense. Oh, that doesn't. Well, how can it not have no size? None of that makes sense. They're under no obligation to make sense because they've been revealed through the methods and tools of science which themselves transcend your senses. And so some of the spookiest features of modern physics reveal themselves as we probe matter on its deepest levels. One of the towering great achievements of the human mind and our understanding of the universe is Einstein's theories of relativity. It's actually, the tenets of it are quite simple, almost scary simple. It makes only two assumptions: that the speed of light in a vacuum is constant no matter who is doing the measurement and no matter what direction you are moving or how fast. You'll always get the same measurement for the speed of light. That's assumption one, which, by the way, experiment has shown to be true. Assumption two, that the laws of physics as you measure them are the same for every observer who would be doing the measuring, provided you are on a vessel that's either moving at a constant speed or not moving at all. Those are the only two tenets that you have to buy into. And all experiments have shown that both of those two tenets are correct. Given those two tenets, extraordinary, spooky phenomenon derived from them. For example, as you travel faster, or if you find yourself in the vicinity of a higher source of gravity, time ticks more slowly for you than it does for other people who are not. It's not just your clock, it's everything about you and your environment slows down. You don't notice this because everything is slowing down, including your neurosynaptic thought rate. So it goes unnoticed to you, but it's patently obvious to everybody else observing you. And this leads us to the famous twin paradox. So here's how it works. Let me get a pair of twins. All right. They're born the same time, they're the same age. And now one of them I will send off at 90% the speed of light. And the other I'll keep down here on Earth. So we can ask, how do their aging rates compare? Okay? Turns out, this twin that I've already sent, his clock ticks 44% as fast as this twin's clock, our clock here on Earth. So, this twin is aging more slowly than this one. That's at 90% the speed of light. Let's pump it up some more. How about 99% the speed of light? Now the time ticks at only 14% the rate, as it does back here on Earth. How about 99.9%? We're getting closer and closer to the speed of light itself. And at that speed, the clock ticks only 4.5% as fast. So, what does this mean? Tell you what it means. This twin that traveled for 5 years and comes back, if they went at 99.9% the speed of light, after 5 years, they're 5 years older. We have aged 110 years. It's called the twin paradox. It's only a paradox if you think about it in sort of classical terms. How could that be? But in relativity, there is no paradox at all. That is a fundamental feature of what happens when all you do is presume that the speed of light is the same for everybody and the laws of physics remain constant. That whole phenomenon is called time dilation. And if you take it to the limit, let's take it to the limit. Is there anything around that actually moves at the speed of light? Sure is. It's not material matter. It's light moves at the speed of light. Photons, the carriers of light, move at the speed of light. So, if time slows down as you approach the speed of light, then the equations tell us that at the speed of light, time stops. That means if you were a photon, time does not pass for you at all. Now that has some freaky, spooky consequences. What that would say is that the instant a photon is emitted anywhere in the universe, typically they come out of atoms or they'll be sent out by a star, the instant it is emitted, it gets absorbed at its destination, if you're the photon. For the rest of us, we're watching it move at the speed of light across the galaxy or across the universe. But to the photon, time does not elapse. Hundreds, thousands, millions, billions of years of our time are zero time for the photon. And I've reflected on this often. I've been on mountaintops with my telescope and a detector, observing the center of the galaxy. That was the subject of my PhD thesis. What was going on 30,000 light years away? And I kept thinking, these are photons that have been journeying for 30,000 of my years. And they come through the vacuum of space, enter Earth's atmosphere, come down, they happen to hit my telescope mirror, focus down on my detector, there they are. And I'm using their existence to help me deduce the nature of the galaxy. Then I asked, did the photon want to hit my detector? If it didn't, where would it land? There's some people laying out on a beach. Some of these photons are hitting people's bottoms, okay? I don't know if that, Imagine being emitted and that's the first thing you hit. Someone's rear end who's sunbathing on a beach. So I felt kind of proud that I could take some of those photons and use them to deduce the nature of the universe, because plenty of other photons would have passed Earth by in search of where they would end up becoming absorbed. And so, such is the plight of the life of a photon, because in fact, since time doesn't tick for it at all, it actually has no life. All that exists about it is what we say, what we do with it when it arrives here. That's a curious duality in the existence of this particle. From its own point of view, the universe goes by in an instant. And for us, we bask in the time it takes for the photon to reach us. What else is spooky in the universe but true? Quantum physics. That wins all prizes for just the weirdest things about nature we have ever discovered. This is a theory of the universe that's been around since the 1920s. In that decade, which by the way was a watershed decade for physics, that's when Edwin Hubble, not the telescope, the space telescope, but the man after whom the telescope was named, that's when he discovered that our galaxy, the Milky Way, is just one of countless other galaxies in the universe. And in that same decade, he discovers that those galaxies themselves are rapidly receding from one another, telling us that the whole universe is expanding. Had they given Nobel Prizes to astronomers back then, he would have gotten at least two. Edwin Hubble, he started out as a lawyer and then became an astronomer. Interesting character in the history of my field. In any event, that decade gave us quantum physics, which, it turns out, is the most successful theory of the universe ever put forth. There is no known edge of its applicability to any problem we've ever encountered. It has worked in every place we've ever used it. Its predictions have shown up to be true every time we've ever invoked them. Meanwhile, there are other what we call successful theories like Newtonian gravity. It works to a point, but then you need Einstein gravity to take it to regimes that Newton never experienced. Quantum works everywhere, everywhere. And there are weird things that go on. Particles also exist as waves, and they can pop out of existence and into existence somewhere else. They don't exist in any tangible way. They exist statistically. Very weird things go on in quantum mechanics, and it is a regime that falls outside of our common sense. So you can't invoke your common sense to decide that what it is you just learned should or shouldn't be true. Take, for example, a sphere that I might pass through a sheet of paper. That's an interesting experiment. Suppose my entire life is just that sheet of paper. What will it look like to me if I pass that sphere through it? First, I'd see a dot. That's the point of contact of the sphere with the page. I don't know that there's a sphere. I just see the page and there's a dot. That dot, what next? It becomes a small circle, and a bigger circle, and a bigger circle. The circle gets to the diameter of the sphere. After that, it gets smaller and smaller again, ultimately becoming a point and then disappearing altogether. That's just weird. If I describe that to you, and I don't know that a sphere is passing through the sheet of paper, you'd think I was crazy. So I'm left wondering, and I'm not alone in this state of mind, whether so much of what we see as quantum mechanics that defies our common sense, that is just crazy, loopy, weird, is actually some sensible thing going on in a higher dimension that happens to be passing through our low dimensionality. I stay awake at nights wondering that. An interesting feature of quantum physics is called tunneling. Tunneling. Well, we learned that a particle can also be a wave. Well, a particle has an existence in a spot. Right? Here's a particle right now. But when you think of it as a wave, the wave can be in multiple places at once. And when you measure that wave, it becomes a particle. And if you measure that wave over here, the particle shows up over here. If you measure the wave here, the particle shows up here. So there's a chance you can measure the particle in any location in the vicinity. Turns out the particle can tunnel through a barrier that it would not otherwise be able to penetrate. That's like me standing next to a mountain, disappearing and reappearing on the other side of the mountain without having to cross over it and invest any energy doing that at all. That's called quantum tunneling. Turns out the very mechanism that drives the energy production of the sun requires it. We had known long ago what the temperature of the center of the sun is. It's about 10 million degrees, give or take. 10 million. At those temperatures, particles are moving very fast. Hydrogen atoms, the sun is made of mostly hydrogen, and their nuclei are protons. They're moving fast. The protons want to resist one another. They're the same charge. And most of the time they do. But in order to fuse them, in order to engage in thermonuclear fusion, thermo is hot, nuclear is the nucleus, fusion is bringing them together. In order to engage in thermonuclear fusion, they have to overcome that repulsion, get close enough to each other until a strong force takes over. In fact, we call it the strong force, the strong nuclear force. That's an attractive force that bonds nuclear particles together, creating bigger and bigger atoms. How do you do that if it's not hot enough to accomplish it? There is a famous British astrophysicist named Sir Arthur Eddington. He said, 10 million degrees is not hot enough, folks, but that's still the hottest place in town. So if we're going to cook elements, figure out a way to do it in there, because I don't know any other place. Turns out, tunneling was the answer. Something discovered in the 1920s when quantum mechanics was fully fleshed out. Some of these nuclei will tunnel across that barrier even though the temperature isn't high enough to accomplish this. Some of them tunnel through the barrier, they bond, they make the heavier elements, and energy is released. The star is born and the star is sustained. So if you look at a cross-section of the sun, right in the center, that's where it's hottest, the 10 million degrees. Some of those nuclei are giving us energy. Credit quantum tunneling for that. High mass stars do this shell by shell by shell. Hydrogen goes to helium, helium goes to carbon, carbon goes to nitrogen, oxygen, silicon, neon. It goes right on down the periodic table of elements all the way to iron. And there's an onion shell structure of all these elements. It happens that those stars go unstable at that stage, and they explode, scattering their enriched ingredients across the galaxy, and those are the ingredients of planets. Those are the ingredients of life. Those are the ingredients of us. All enabled by quantum mechanical tunneling. Just showing up across a barrier where you had no business being. When I think of light, we know light has a speed in a vacuum. It's a constant. Einstein told us that. All measurements show this. Did you know, however, that when you put light into a medium, a transparent medium, the speed of light slows down? It slows down. Not only that, it bends. And the bending of the light, we call that refraction, can send the colors of the light into different angles because those different colors themselves travel at different speeds. That's how you make a prism. That's what goes on in a raindrop when sunlight through the raindrop makes a rainbow. Isaac Newton showed that white light is composed of 7 colors. We call it Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Actually, I only see 6 colors. He had a mystical fascination with the number 7, so he threw in a 7th color just around, and that was indigo, of course. But it's really red, orange, yellow, green, blue, violet All right? So there are these colors. White light is composed of those colors. You take that white light, pass it through these media. The red travels at a different speed from the orange, from the yellow, from the green, and it all spreads out, and out comes the beautiful rainbow. Beyond light and the colors that it makes, what is most astonishing to me, and we've known about this since 1905, so this is not new, but every day I think about it, my jaw drops open, and that's the equivalence of mass and energy. An equation first written down by Albert Einstein in 1905. You learned it in elementary school. E equals mc squared. The c is the speed of light squared. It's a constant. Don't worry about that. All that matters in that equation is that energy sits on one side and mass sits on another. And we've known about this in Cold War politics because our entire nuclear arsenal depends on that formula, creating energy out of matter in a bomb. Okay. And the sun does it every second of its life. So does every star you see in the night sky. We don't have an everyday experience with E equals mc squared. That's a good thing. But if we had very sensitive measuring devices, we would. For example, if I take a spring and I stretch it, I'm actually pumping energy into the spring to hold it in a stretched position. If you figured out how to weigh that spring in before and after situations, you'd find out that the stretched spring weighs more than the unstretched spring because I pumped energy into it, and that energy has mass. The energy has mass. It'll show up in a spring. It'll show up in a rubber band. It'll show up when you stretch a rubber band. It'll show up in chemical powders like gunpowder. That's stored energy in the molecules of gunpowder. Gunpowder weighs more because of that stored energy than it otherwise would if you broke apart those molecules. Not only that, gasoline weighs more simply because it has stored energy. And so when I think of all that drives the universe, when I think of what makes the universe tick, you part the curtains, what's behind it all, you will find the equivalence of mass and energy. That equivalence of mass and energy drove phenomenon in the early universe, in the Big Bang itself. It drives the energy production in every star you see in the night sky. It was responsible, like I said, for the geopolitics of the Cold War. All by that one little equation, making so much sense of what goes on in the world. And of the many things that prevent me from getting a good night's sleep, one of them is there another equation like E equals mc squared just beyond our reach? Because we are still steeped in profound ignorance of what's going on in the universe. There's a lot we know, proud of that, but there's even more that we don't know. Is there some equation like E equals mc squared that we haven't seen yet? If it's there, is it just out of our reach, or is it not just out of our reach? Do we have to climb several mountains before we even get to the point where we see the next equation that can transform the next generation's understanding of how this universe works? I don't know. But what I do know is E equals mc squared explains so much of what's going on in this universe. It actually makes us feel a little cocky about it. It's like, yeah, we're there. We got it. But the march of science tells us, just when you thought you understood something, the universe throws you a curve. You know, Hollywood is not the first place to start dreaming up aliens and wondering what they might be like. We're all entertained by them, of course. You know, some amount of intellectual energy goes into asking, what do they look like? Where are they from? How'd they get here? Do they eat? But they're not the first. This is a long time-honored pastime. It's been going on for centuries. In fact, let's go back to an example of this in the 17th century. Brilliant scientist, Christian Huygens. He's a Dutch physicist, astronomer, mathematician, philosopher, a Renaissance man. And his resume includes the fact that he invented the pendulum clock. Somebody had to do it. Not only that, he was the first to study Saturn's rings through a telescope, to the point where he identified them as rings. Before Huygens, people just saw this blobs of light near the ball of Saturn, not knowing what they were, not knowing how to interpret what they saw. Just two items on a very long resume that this fellow has. Now, the late 17th century was a time when Newtonian physics was just taking root. It had been around for a few decades, but it was well tested, and everybody was had bought into it. Yet biology was still a fledgling academic field. In his great work at the end of the 17th century, published 1696, The Celestial Worlds Discovered, he drew an analogy between Jupiter and the Earth. In that analogy, he noted, of course, that Jupiter has an atmosphere, just as Earth does. And if you have an atmosphere, then maybe you have weather. Well, if you got weather, you're going to have rain. And if you have rain, you might have oceans. And if you've got oceans, you can now think about what life might want to do in the presence of these oceans. If you were life on Jupiter, you'd want to get around somehow. So what would you do? You'd have boats, of course. And how would you navigate? Well, you'd have sails. How would you control those sails? You would need some mechanism to do so. You'd need rope. Well, if you've got rope, what would that rope be made of? So from all this line of reasoning, he deduced that any life forms on Jupiter would be growing hemp. It's charming, but it shows a deep sense of caring for what life might be like elsewhere, and built into it is actually a cultural bias that we almost can't avoid, because all we know is ourselves when we think about other life in the universe. And that cultural bias puts our own values and our own technologies onto what others might have to enable them to get around. And not only this, you look at the opening chapter of The Celestial Worlds Discovered, and it's a celebration of Newtonian physics. It's complete with very well understood planetary orbits. It's got the sizes of the orbits, their shapes. It talks about how bright the planets are, and it makes some judgment about how rocky they might be. And not only that, the book has like a fold-out chart that actually gives the layout of the entire solar system. And in that discussion, in fact, there's no mention of God. Even though just a century earlier, Newton's laws of physics, Newton's understanding of gravity and motion had not yet been invented, had not yet been discovered. And so the planetary orbits were mysteries back then. So here, where there is no mystery to Huygens, there is no mention of God. Meanwhile, when he speculates about life in the solar system, he raises questions he cannot answer. And he lists the biological mysteries of the day, such as the origins of life's complexity. Now, sure enough, because 17th century physics was more advanced than 17th century biology, Huygens invokes the hand of God only when mystery prevails. I suppose nobody will deny, but that there's somewhat more contrivance, somewhat more of miracle in the production and growth of plants and animals than in lifeless heaps of inanimate bodies. For the finger of God and the wisdom of divine providence is in them much more clearly manifested than in the other. I think the lesson here is Yes, we'll always be confronted with mysteries. Always. In this particular case, he's imagining what life would be like elsewhere. He knows he likes to get around, and what's the way you get around back in the 17th century? You travel vast distances by taking a ship, a sailing ship. He's imagining aliens with sailing ships. Today, what do we imagine our aliens do? They're not sailing, they're taking spaceships, because today we have spaceships, leaving me to wonder, several centuries from now, what new aspect of our culture and our civilization will we be imparting upon the priorities and transportation needs of aliens of the future? The most challenging question you could ever ask in a scientific inquiry is, what is the origin of a thing? And it's challenging whether or not the question involves life. It's for an obvious reason. Nearly everything we ever study already exists. And so you can study its past, you can look at it in the present, and you can maybe extrapolate to the future. And in so doing, you build a timeline of its life. Right? So that works. But how about the start of it? How about the beginning? How about the transition between it not existing and existing? So in the universe, knowledge of our sun's birth would ordinarily be completely inaccessible. Because how are we going to get back there and then? We can't. Fortunately, billions of stars in our galaxy exist in all phases of life and death. So we can use them as proxy for our thoughts about the sun. We can infer how the sun was born, and we can infer how the surrounding planets were born here by looking deep within massive clouds of gas and dust in our own galaxy. That requires special telescopes, of course, to not only see the surface of the clouds, but use wavelengths of light that dig deep down and see where all the action is. But with life on Earth, as far as we know, there was only one Genesis. And if there's only one, there's not another way to compare other forms of life that were born separately from ours, that have different origins. Let's go back then and imagine, at some point there was a conversion of inanimate organic molecules, comprising elements such as carbon, hydrogen, oxygen, nitrogen. These are the traditional elements of what we call organic chemistry. At some point, there was a transition of inorganic molecules into animate, self-replicating creatures. That would have happened about 4 billion years ago. And that transition today remains inaccessible to us. And as a consequence, remains a mystery. All right, because of this, it greatly challenges our efforts to duplicate the phenomenon in the laboratory. We don't see it happening it could be, but we don't see it happening anywhere else. Now, the modern tree of life has a level of depth and complexity that Darwin and perhaps even your parents' biology teachers wouldn't even recognize. As far as we've ever measured, all life on Earth has common genetic heritage. That's what the tree of life means. Everyone branches from, you go back in time, there gets fewer and fewer branches, and you reach a point where there's only a single branch. So, an example of this, dig far enough back in time, and you will find the common ancestor between any two people on Earth, the common parent. Dig far enough down the tree of life, and you will find the common ancestor to any two species on Earth. I don't care what they are, you can find it. How about humans and chimps? That's in the recent past. How about humans and goldfish? That's a little farther back. How about humans and toadstools? Humans and yeast cells? There is a point where you will find the common ancestor for any two branches of modern life. And so, as far as we've been able to determine, there's been only one Genesis on Earth. So, in order to help out this effort to understand life and how it got here, what we need is a second Genesis on Earth, or an ensemble of planets out there, all with different stages of formation of life on them, just as we've done for the formation of stars and planets in the galaxy. This is some of what motivates the search for other planetary systems out there. If we find them with life, let's get the inventory of them all and compare and contrast. So, what we need to ask, however, is, on Earth, since life happened pretty quickly, almost as quickly as it could have, took place within a couple of 100 million years, why hasn't there been a second or multiple coexisting parallel trees of life on Earth? All data that we've ever collected on the fossil history of life on Earth tells us that life began almost as soon as earthly conditions would allow it. For the first 500 million years or so of Earth's 4.5 billion year history, the planet was still forming. It was still accreting leftover material from the nascent solar system. We call this period the period of heavy bombardment. And the word accretion, that's what we say in astrophysics. That's just a polite word to describe the incessant impacts of comets and asteroids and planetesimals. These are planets that are not yet grown, but they hit you and then they're gone and they're part of your material rather than another planet that might have formed out there, right? This is the process of Earth clearing its orbit, rendering Earth's surface hot, because every time one of these objects hits, the surrounding terrain heats up. And under those conditions, under those temperatures, you cannot form complex molecules, because large complex molecules break apart in the presence of heat. And after all, what is biology if it's not the most complex expression of chemistry we know? So now, after this period of heavy bombardment, it took no more than 200 million years. That sounds like a lot, but it's not. It's just 0.2 billion years of Earth's history. Start the life clock after the period of heavy bombardment and ask, how long does it take to get the first evidence of life on Earth? 200 million years. That's after Earth cooled to allow the formation of complex molecules in the first place. So I'm tempted to ask, if life formed so quickly back then, practically as soon as it possibly could have, then why wouldn't life keep forming in this fertile newborn Earth? Why wouldn't there be multiple genetic origins of life? Why not multiple coexisting trees of life, forming, dying, and forming again? A lot of time has passed since 4 billion years ago. If it did happen, if there were coincident trees of life, there's no trace of it. And if it did happen, our tree of life was far more successful at exploiting Earth's resources than any other tree of life that might have been competing with us. And in the end, it is our tree of life that won. We weren't around back then. Fossil evidence tells us about only one tree of life. So, the end we really don't know. You know, one of the branches in the tree of life that's established just in the past couple of decades is the community of organisms known as extremophiles. And as the name implies, these are lovers of extreme environments. And these are the kinds of environments that we humans would find hostile to our comfort. Long gone is the time when we imagined all life on Earth requiring a warm, room temperature pond in which to evolve. Extremophiles, they thrive in high temperatures, low temperatures, high acid, low acid, high pressure, low pressure. All kinds of extreme environments, these organisms do just fine. Just fine. Now, put a pin in that and consider that recent computer simulations of asteroid impacts on planet surfaces tells us that surrounding rocks can be cast into space, escaping the gravitational pull of the planet on which they were found. That's an interesting fact. Put a pin in that fact as well. Now, you've got the existence of extreme microbes, microbes that can thrive in extreme environments. You have rocks that can be cast into interplanetary space, allowing them one day to land on other planets, given enough time. Calculations show that, for example, Mars rocks have come to Earth. Earth rocks have gone to the moon and to Mars, and so forth, back and forth around the solar system. Now, there's evidence for liquid water on early Mars. That evidence is plentiful. Mars is bone dry today, but look at the surface features. They're dried riverbeds that meander, and they're floodplains and lake beds, all bone dry today. Bone dry. Something bad happened on Mars. We don't know what, but something bad. In its day, however, we expect Mars to have been an oasis. So, it may be true that Mars was wet and fertile long before Earth was. If so, then maybe, just maybe, there was stowaway bacteria on Mars hiding in the nooks and crannies of the rocks that have been cast back into space. Some of those rocks may have made the journey from Mars to Earth. Now, let's say it had a full assortment of microbes. Microbes that actually like warm ponds, as well as microbes that can thrive under stressful conditions. Then only those microbes that survived the cold, dry, radiation-intense void of space would have survived, seeding early Earth with life, seeding early Earth with extremophiles. We call this concept panspermia, and it implies, if true, that all life on Earth are descendants of Martians. So all this leads to a couple of interesting questions, I think. Suppose we find life on Mars and it's DNA-based. All right, it could be one of two possibilities. Either that life has DNA in common with life on Earth. That's the smoking gun that we are Martian descendants. But suppose it has DNA and there's no genetic code in common. What that will tell us is that DNA may be a fundamental molecule of life. And if we were to find life anywhere else, it would be based on DNA. It just wouldn't have any DNA in common with us because it didn't co-evolve here. So, what would be more interesting, I think, is if we go to Mars and we find out it has life and the life is not even based on DNA at all. That's a much more interesting result, personally, because that would then give us another way nature figured out how to make life. And it would tell us that life, in fact, doesn't require DNA. It found another way to encode identity, to figure out how to make one creature different from another. When you add all this up and dig deeper, what you find is that life on Earth, it's not simply are we based on DNA or not. Of course we are. But there's something else that's true, hardly ever talked about. And that is the fact that complex molecules, nearly all of them, have a kind of handedness. They're not the same on one side of a mirror as they are on the other, yet they're chemically identical. So as an example of this, if you take a glove, a left-handed glove, and you look at the left-handed glove in a mirror, that glove in the mirror is a right-handed glove, and vice versa. So it's possible to have a chemical that's written out, that's identical to another chemical written out, but when you build it, it looks different in a mirror than it does on your side of the mirror. A famous example of this, my favorite example of this, is the molecule for the flavor that you detect as spearmint. If you write it down, it's identical to the flavor of caraway. Same number of atoms in the same sequence. But one of them is constructed with a left-handed orientation and the other with a right-handed orientation. And our body's tasting mechanisms distinguishes the two flavors from one another. And of course, spearmint and caraway, those two flavors taste nothing like one another. There's nothing related between one and the other, yet it's the same molecule. Turns out life is overwhelmingly left-handed. Organic molecules on meteorites, because in fact, organic molecules can form in interstellar space and intergalactic space and interplanetary space. We see these molecules across the universe. When we find organic molecules in meteorites and ask how many of them are left-handed, how many of them are right-handed, it is 50-50. Yet those same molecules, when we look in life on Earth and find them, and we bin them by who's left-handed and who's right-handed, 100% of them are left-handed. So it leaves you wondering, could there be another planet out there, just like ours, except everybody uses right-handed molecules? That's kind of an interesting question. Or why isn't there an entire coexisting ecosystem on Earth that thrives in this right-handed regime? Then we can ask, and it's not well studied, we can ask, does one kind of handedness offer an advantage, an inherent advantage over the other, either in competing for resources or maybe two forms of life, if one doesn't interact with the other, it could be that you could not derive nourishment by eating the right-handed life versus the left-handed life. That'd be an interesting planet to live on. You'd have to know in advance who your prey was. Is it left-handed or right-handed in its molecular construct? That's a science fiction movie waiting to be filmed, a book waiting to be written. That's one I'll buy. I've got another question. How smart are humans? It's funny because we're the ones doing the defining. And so if we define what it means to be intelligent, then how accurate could that be on a cosmic scale? You know, when we search for intelligent life in the universe, we try to set up criteria by which we would judge this civilization to be intelligent. And the audacity of us to presume that we'd even be able to meaningfully communicate with this species of life from another planet. Now, why do I say that? Because we can't even, we can't even meaningfully communicate any kind of deep ideas with any other species of life on Earth. And life on Earth are creatures with whom we have DNA in common. And my point is, in spite of whatever conversations you think you're having with your dog, I'm suggesting that they're not deep. They're not the kind of conversations you'd imagine having with an alien. And so I question the audacity of saying we're intelligent, any other intelligent species out there will be able to have a conversation with. That's audacious. In fact, it's hubristic. Let's explore this. Let's explore what this means. All right. Let's compare human intelligence as we define it to chimp intelligence. All right? Use our own definitions of this. Right? We have nearly identical DNA with the chimp. And it's trifling difference. It's less than 1% difference in the DNA between a chimp and human beings. Okay? By the way, this comparison can work with any other animal. All right? It'll just be more illuminating if I compare us to chimps. I could compare us to dogs. All right? But I'm just using chimps because they're the closest relative. All right. So, 1% difference between us. And we say to ourselves, what a difference that 1% makes. All right? We compose poetry. We have philosophy. We have technology. We've got Beethoven's Ninth Symphony. We've discovered quantum physics. We built the Hubble Space Telescope. Yet what can the smartest chimps do? You know, they do what human toddlers can do. Maybe they'll be good at some rudimentary sign language. Maybe they can stack boxes to reach a banana or some other object of interest. Our toddlers can do that, yet that's the behavior of the smartest chimps that are out there. Again, we're defining what's smart. All right. Now, imagine, if you will, a species of life, an alien species perhaps, likely, that has 1% genetic intelligence beyond ours, just as our intelligence is 1% genetically beyond that of the chimp. What would we look like to them? Frankly, I think we look like drooling, blithering idiots. That's what. All right? If it corresponds, then the smartest among us would be capable of what their toddlers can do. Imagine their human researchers sort of rolling out Stephen Hawking and commenting, hey, he can do astrophysics calculations in his head, just like little Timmy over here in preschool. That's what they'd be saying about us, because that's what we say about chimps. Imagine, I could keep going here. Imagine they're preschoolers. They bring home their freshly composed operas for the refrigerator door instead of, what do we bring home? Pasta collages, all right? Their preschoolers will bring home fresh derivations of calculus instead of finger paintings. Would that species judge us to be intelligent at all? Would they enslave us? Put us in a zoo? Would we even know it if they did it? In fact, is Earth a zoo for their own entertainment? If they're that much smarter than we are, this would be a trivial exercise in their culture to accomplish, because we do that for other creatures that are not as smart as we. Now, perhaps the most terrifying thought of them all is that such a species is out there, such a species has combed the galaxy in search for intelligent life, such a species has visited Earth, observed our ways, our cultures, and concluded, based on all the data they have gathered on us, living here on Earth, that there is no sign of intelligent life. Remember the periodic table of elements? That's that mysterious chart of boxes that hung in your chemistry class. Well, you might not know that there are still mysteries about the table that befuddle even chemists and physicists. For example, at the heavy end, these are the elements that we're actually manufacturing in the laboratory. We've found all the elements that nature has to give us. Now, to extend our understanding of the table, we are creating elements beyond what nature is capable of all by itself. And there are places there that remain mysterious to us. But let's back up for a minute. The structure of the table, just as a quick primer, you have columns. And as you go from left to right, an extra electron gets added to the outer shell of that atom. The rightmost column holds 8 electrons, and that completes the shell. When you have a completed shell, you have no electrons to either give or take. And when you have nothing to give or take, you cannot make molecules with any other atom. It's an interesting part of the diagram, but all parts of the diagram have interesting things to talk about. For example, you remember that elements that are in a column have the same number of electrons in their outer shell as each other. What that means is they will bond similarly with the same set of other atoms. Best example there is carbon and silicon. There's a good example. We are carbon-based life. Our entire biochemistry is based on carbon. Right below it is silicon. So you can ask the question, if you can have carbon-based life, why couldn't you have silicon-based life? In fact, there's a famous episode of Star Trek, the original TV series, where they imagined a silicon-based life form. Now, silicon is one of the active ingredients in rock. Okay, so rock is pretty stable. So here we have this rock. So they imagined silicon-based life as a rock moving around that could penetrate through mountains the way we humans move through air. It's a cute storyline, but it turns out, while that maybe life based on silicon is possible, it's just not necessary, because carbon is far more abundant than silicon in the universe. And also, its bonds are not as permanent. If you have permanent bonds, it restricts how much chemical experiments nature can do with your molecules. And so with carbon bonds, they can break, they can reassemble, break and reassemble again. Much more experimenting that can happen with that. And that's what you need when you want to try to create life. When you want to create the complexity that we know exists in life. In addition to shells of electrons that exist in the atoms on the periodic table, the nucleus of each atom has a shell structure as well. Now, the nucleus is composed of protons and neutrons, and it depends on how many protons and neutrons are in each shell will determine whether or not the atom itself is stable. If a shell is complete, you've got a stable atom. If the shell is incomplete, it's more likely to decay into lighter elements, breaking apart into other elements on the periodic table. That is the origin of radioactivity. Now, those elements with a complete outer nuclear shells and complete electron shells, they're the most stable elements of them all. Now, all known elements that are heavier than lead are unstable. And generally, it's a general truth that the larger the nucleus, the less stable it is. How unstable? They last fractions of a second, maybe at most a couple of minutes at a time, before decaying. Currently, we've discovered elements in nature up to 92 protons. That 92nd proton element, that's uranium, named, in fact, after the planet Uranus. And beyond that, we've manufactured another 24, heavier than uranium. Where would we do that? Of course, in the physics laboratory. Now, the most recent of the named elements has 112 protons, manufactured in the lab. It's called copernicium, named, of course, for Nikolai Copernicus. He advanced the sun-centered model of the known universe back in the mid-16th century. Finally caught up with him, honoring him with an element name on the table. Now, most models of nuclear structure tell us that elements with 120 protons or 126 protons and 184 neutrons might be stable on timescales that are long enough that they could survive days, maybe even centuries. We've made elements up to number 118, and so we're right on the threshold of this magic island of stability. Haven't been there before. We think it's there, and this is counter to the traditional sense that big, fat nuclei are unstable. Our models tell us that you can have a community of massive nuclei that are as stable as anything else in our lives. Now, if we reach that zone, what might we use these elements for in everyday life? Maybe they're so exotic, they'll just be curiosities. We've been there before. That was said of most of the elements that were discovered on the periodic table. For example, who would have thought that germanium, which is an obscure semi-metal discovered in the 1880s, would turn out to be the crucial ingredient in the development of transistors, that 70 years later? Or how about elements like neodymium and samarium? They were regarded for a century as just curiosities. They turned out to be essential to the construction of super powerful permanent magnets. Or one of my favorites is americium, named for America. We discovered a lot of elements down there, and so that's one in honor of America. That one was discovered in 1944, americium. That would ultimately become, and is today, the active ingredient in household smoke detectors. So, I look at this island of stability and I hunger for what properties they will have. And in the hands of a clever engineer and perceptive scientist, we'll be able to exploit those properties and possibly transform life as we know it today. Where were you in the 1970s? Were you even born yet? And if you were you dancing to disco? That's what I was doing. I was the right age and at the right time. But over that decade, physicists in America and in Europe were getting the final inventory of all the known particles in the particle zoo. And it wasn't just the compilation of an inventory. What came out of that period was an understanding of how all these particles fit together in a coherent way to think about the relationship of particles to each other and the relationship of particles to matter and to the universe at large. So what we've come to learn with the help of high-energy particle accelerators, and what do? Their job is to smash atomic nuclei together and pick up the pieces that come afterwards. And when you smash nuclei together, there's a lot of energy that gets pumped in. And that energy can spawn new particles. Other particles can disappear. And it's a mess. It's a train wreck. But out of that train wreck, you get insights into the nature of matter. And you can see what the universe has wrought in the center of your particle accelerator. And what we've come to learn is that there are 3 energy regimes of matter. 3 of them. There's the low energy regime, the medium energy regime, and the high energy regime. Guess which one we're a part of? The low energy regime. Sorry about that. So everything we know, everything we do, think about, say, taste, touch, occurs in this low energy regime of particles. We are wholly unfamiliar with the other 2. And so let's take a quick look at the inventory of what particles thrive in that low energy regime. First, we have our protons and neutrons, all right? Turns out they're not fundamental particles. They're not. As we said earlier, they're made of quarks. We call those quarks up and down. Okay, that's kind of funny because you go back to ancient Greece, the word atom was invented to describe an indivisible part of matter. Atom means indivisible. We would later find that atoms are composed of particles, and in this particular case, neutrons and protons are themselves divisible into quarks. So we have the up quark, the down quark. What else do we have? We have the electron. We're familiar with electrons. That's what courses through all of our electronics in this modern era to give us what we call electricity, the electron. Then there's another particle, a particularly elusive particle. We've greeted it before earlier in this series. It's called the neutrino. And that particular neutrino is an electron neutrino. You get one of these by an interesting way. Go snatch a neutron from the nucleus of an atom and leave it out in free space. 6 minutes later, it decays. Neutrons are not stable outside of nuclei. Now, a neutron has no charge, but it decays into 3 particles, a proton, an electron, whose charges cancel each other. So you start with no charge, you end with no charge. The neutron becomes the proton, the electron, and an electron neutrino, which escapes. It escapes. So there you have it. Up quark, down quark, electron, neutrino. And of course, they each have antimatter counterparts. Antimatter. We invented antimatter, not the science fiction writers, this favorite fuel of space travel in science fiction stories. Antimatter does exactly what you think it does. When it comes in contact with matter, it annihilates, creates pure energy. Antimatter is real. It's made every day in particle accelerators. You find it every day in the centers of stars. It is part of the particle count that we inventory for the universe. So what we have are a total of 4 particles and their antimatter counterparts that makes up our regime of energy in this universe. I repeat, 4. Those 4 particles comprise everything you have ever seen, done, thought about, tasted, sat on, touched. Up quark, down quark, electron, and neutrino. All right. Each of those particles has a corresponding particle in the other 2 energy regimes. So let's go to the middle regime. What are the 2 quarks? Well, they have fanciful names, like ours were up and down. The middle regime quarks are strange and charm. And there's a counterpart to the electron we call the muon. And of course, the muon has its own neutrino. We call it the muon neutrino. Third up, in that 3rd energy regime, we get 2 more quarks, the top quark and the bottom quark. And we have a 3rd species of electron. We call that the tau particle, and the corresponding tau neutrino. That's 3 generations of quark pairs, 3 generations of electrons, and with their corresponding neutrinos. Now, operating among these particles are 3 other particles that transmit forces, okay? 3 other particle groups that transmit forces. You have the photons that transmit electromagnetic forces. You have the gluon, my favorite particle name of them all, the gluon that transmits the strong nuclear force. That's that force that's so strong it holds protons together in the nucleus against their wishes. And in fact, the gluon holds quarks together inside the protons and neutrons, okay? The gluons. Third, there's something called the weak nuclear force, and those are propagated by what we call the W and the Z particles. And there are more physicists who are not Americans than are Americans, and so they pronounce it in the way that the British say our letter Z. So it's called the W and the Z particle, all right? Now, add to this the Higgs boson. The Higgs boson, sometimes called the God particle. How audacious. What could possibly be godlike about this one particle? Well, people reference it as the particle that creates the field that grants mass to all other particles. It gives them mass. In an interesting way, it creates a field and a particle tries to move through the field, and if it feels resistance, more resistance it feels, we measure that as high mass. And if the particle goes through freely, we measure that as low mass. The Higgs boson, granting mass to all other particles. So that, ladies and gentlemen, is the standard model of particle physics. The standard model. Throw in gravity. I haven't mentioned gravity yet. Throw in gravity, and this inventory encapsulates all of the universe that we understand. All of it. All of it. But I got to sit down for this because there's some questions that I'm left with after we go over this inventory. I wonder, why? Why are there 3 regimes of matter and not 1 or 10? Why is there 3? Why do particles have the properties that they do? And why are there particles at all? And are these particles fundamental? We think they are. Or do they themselves have an as yet unresolved, never-ending internal structure deep down within them? Or perhaps, most intriguing of all, is there a simpler understanding that continues to elude us? Maybe there is a deeper understanding of the universe that awaits us, simultaneously eluding us. Right now, there's a whole team of people thinking about that very problem. They're called the string theorists. The string theorists. And what that idea offers is the hope, among other hopes, it offers the hope of unifying all the particles and all the forces of physics. Now, why would anybody want to do that? If our descriptions of nature work, what's the need to try to simplify that even further, other than just the elegance of it? Well, this exercise, this urge to combine all the forces of nature and all the particles into one single coherent understanding has been a kind of a holy grail ever since the beginning of any understanding of particles in the first place. And in fact, one of the early leaders in this exercise has been what was Albert Einstein. After he did all his great work with relativity, he devoted most of the rest of his life to what was called the unified field theory. This was his attempt to bring together all the pieces of physics into perhaps something represented by a single equation. Now, there's good precedent for this, by the way. In the 19th century, electricity and magnetism were presumed to be separate and distinct entities until they were shown to occupy 2 different sides of the same coin. When we discovered this, electricity and magnetism got stapled together into one word, and that's where we get electromagnetism from. It wasn't always one word. It started out as 2 words back in the 19th century until we learned more about the structure of matter and the behavior of nature. Meanwhile, in the late 1960s, early 1970s, the electromagnetic force was found to share the same coin with the weak nuclear force. What came out of that? A new theory of our understanding of the universe that combined those 2 forces. So now we do some more stapling, do some editing. We had electricity, magnetism, became electromagnetism. We have electromagnetism and the weak force. So rather than have a word this large, it's called the electroweak force. So why not continue in this grand tradition until we learn of the one force of nature from which all else derives? Why not? Okay? But that's got to be a cool result, all right? Now, think about it. There's no tablet in the sky that requires that the universe that we live in, regardless of our perception of it, that it exists in 4 dimensions and only 4 dimensions. That'd be 3 spatial dimensions, X, Y, and Z, and of course, the time dimension, T. In the past several decades, basically since the dawn of string theory, it's been imagined that all the fundamental particles that we see and measure are not separate and distinct from one another. It's been imagined that they just appear that way to us in our lowly 4 dimensions. Our lowly 4 dimensions. You never heard anybody say that, right? our lowly 4 dimensions. Perhaps that's what's really going on, because in higher dimensions, the string theorist tells us, exist these vibrations of strings of energy. And that string is what's fundamental, not the particles themselves. Particles are just manifestations of those vibrating strings in our dimension. And if you vibrate a string at one frequency or another, it reveals itself as one particle or another in our dimension. Now, there's not a shred of evidence to support this idea, nor is there any proposed experiment that can test it within the foreseeable reach of modern technologies. But I'm okay with that. I'll overlook that shortcoming for now. One of the great mysteries of the universe, just because it's just so cool, is what is the nature of black holes? Black holes. Kids love black holes the way they love T-Rex. And I think it's because each of these entities can eat you. And anything that eats you, you give your highest respect. Black holes. You know, they're the consequence of the general theory of relativity of Albert Einstein. And that's his theory of gravity. It's the modern theory of gravity. And it describes gravity not as a force, the way we normally come to think of a force, action at a distance. Gravity is the curvature of the fabric of space-time. Space-time, that's our coordinates in space combined with our coordinates in time. That sounds exotic, but it isn't really. For example, you've never made an appointment with someone at a place unless there was also an agreed upon time. And you've never met someone at a time unless there was an agreed upon place. So the intersection of space and time has been with us our entire lives. It's even in our language. It's just not in our thoughts. These are fundamentally interwoven concepts, space and time. And this whole general theory of relativity concept leads us to the fascinating statement uttered by the relativity community, and it summarizes what goes on. It's that matter tells space how to curve, and space tells matter how to move. Now, what that tells you is that regions of space can have such high gravity that the curvature of space is so deep within it that if anything wanted to climb out of that curvature, it can't. Can't. What's the limit on that? It turns out there's a kind of zone where even if you're traveling at the speed of light, that is insufficient energy to leave the area, to leave the zone. If you are in such a zone and light doesn't get out, and light is the fastest thing we know about, nothing gets out. It is dark and it is a hole. That is what we call a black hole. Now here's what's interesting about that. Here I am on Earth. I can take a pebble, toss it up, it comes right back. If I throw it faster, it'll go higher before it comes back. There is a speed with which I can toss this such that it will never come back to Earth. You can calculate what that is. You can experiment. We've demonstrated it with the missions to the moon. It is 7 miles per second. Now, I'm not strong enough to do that. But I promise you, if I threw this 7 miles per second, it will escape Earth and never come back. That's the escape velocity of Earth. If you have an object that is approaching the dimensions of a black hole, that escape velocity gets higher and higher and higher and higher. And just the way I can play catch with this pebble or with a ball on a very high gravity surface, you can play catch with a beam of light. Because such is the path that the light takes through the heavily curved space-time in the vicinity of a black hole. Now, that makes for some interesting phenomena. What would happen if you fall into a black hole, you might ask? If you didn't ask it, I'm asking it for you. What would happen if you fell in? Well, let's take a feet first dive. All right, so you're falling in, there you go. Here's what happens. The center of the black hole, the gravity is so intense that as you get nearer and nearer to the center, because you're falling right now, you get nearer and nearer to the center, the difference in gravity between your feet and your head begins to grow. The difference in gravity. Because the rate of change of gravity is so severe as you approach the center of the black hole. So that difference in gravity we call the tidal force. And tidal forces have the power to stretch things. The moon's tidal force on Earth stretches the oceans, creating tidal bulges. So when you have high tide, low tide, Earth is turning into and out of these bulges that are always there in space. People say, just a quick aside, the moon affects tides on Earth. Does it affect our heads? Because the tides are water, we're mostly water, the biologists tell us. Yeah, there's a tidal force across your head. It turns out it's 1/trillionth the force on your head that the pillow that you slept with would put on your head if your head happened to be under it. So we have tidal forces. They're especially great across large objects and especially small across the diameter of your head. All right, so here we are falling into the black hole. My feet want to approach the center faster than the top of my head, and I begin to stretch, and I get longer and longer and longer. Stretching feels good initially, but at some point it hurts. And you reach a point where, in fact, the tidal force is greater than the molecular bonds that keep your flesh together, and you snap into two pieces, likely at the base of your spine. After that, those two pieces feel the tidal force, and they snap. So you go from 2 to 4 to 8 to 16. And this continues all the way down to the center of the black hole, where you become a stream of atoms. And that's not even the worst of it. Because space-time is funneling down to a point, you are not only being stretched, you are being squeezed, shoulder to shoulder, front to back. You're being extruded through the fabric of space-time like toothpaste through a tube. We have a word for this, a word for dying while falling into a black hole. It's called spaghettification. Because that's what you look like, a string of spaghetti falling in. So, it turns out, very large black holes, the tidal force is not as great as small black holes. Because big black holes, your feet, while they're closer to the center, the difference between your feet and the head is not that great. So it turns out you can survive a fall into a black hole. Now here's the kind you want. You want to spin up the black hole and fall into one where when you get inside, the singularity is actually a donut shape. That's what happens when you have a spinning black hole. It takes on extra interesting properties. As you fall into a black hole, time slows down, and to a point where it practically stops. And when it stops, the entire universe that you just left unfolds in an instant, and you see the future of the universe you left in the instant it takes you to fall down into the black hole. This is clearly a one-way trip, okay? Can't tell anybody else about this. But we also learned that you do the calculations for what you expect to find in the center of a black hole that's rotating. There is an entire other space-time that is opened up before you. An entire other universe that's not the one you just came from. So, take a large spinning black hole, fall in for this one-time experiment, and you may end up in another universe entirely. Have we ever done that experiment? No. It works on paper. So we'll accept volunteers. Anybody out there want to verify that prediction? You never know what's going to cause the next great discovery to be made. Is it a eureka moment in the middle of the night? Is it some small inconsistency in a measurement that you made? Isaac Asimov famously noted that the greatest discoveries in the history of the world weren't somebody burning the midnight oil saying eureka. It was somebody looking at some data and saying, that's odd. So consider that in the late 1800s, classical physics was riding high. What is classical physics? It's Newton, it's electricity, it's magnetism, it's all of these sort of basic laws of physics that were established between the 1600s and the 1800s, all right? Definitely before the quantum and before relativity and all these exotic theories of the universe that defy every bit of common sense you could possibly bring to bear. So there's some well-known scientists at the end of the 1800s, and they were sure that there were no more major discoveries to take place in the field, and that physics would soon end. There were just a few messy clouds on the horizon that some better research would resolve. Would say these differ from each other. Do the experiment again a few times, and that'll all come out just fine. Coming out of the 1800s, however, those small clouds turned out to be more like sort of chinks in the armor of classical physics, which eventually opened a door into a century of mind-blowing modern physics that transformed the world. Not only the world of physics, but geopolitics as well. The simple introduction of E equals mc squared as the foundation of all of our nuclear arsenals, how they generate energy. So small things that don't quite work. Some of them get resolved with better data, others don't. They lead to deep and new understandings of the universe. And so in that spirit, I bring to you a story, something we call the Pioneer anomaly. There are two spacecraft, Pioneer 10 and 11. They were launched in 1972 and 1973. And they were destined to take a tour of the planets and escape the solar system altogether. And the way you do that is, because our rockets aren't big enough to give it that much energy. So they launch and they come in behind a planet and they fall towards it, and the orbit of the planet catches on to the space probe. And then you do a sort of a gravitational slingshot, flinging it forward with extra energy. When you do that for a couple of planets, you can have enough energy to have those space probes escape the solar system altogether. They were the first ever pieces of hardware to achieve this feat. And because of this fact, we had affixed on their sides a famous plaque of pictograms. It showed, among other things, an unclothed male and female human form. And the male, you may remember this from the day, and the male had an arm raised, presumably a sign of peace. That assumes that this is a sign of peace to aliens, of course. But on this plaque, there was a map that showed where the craft came from, which is essentially the return address of the solar system in the galaxy. And not only that, it showed some other basic scientific insights that we've gleaned as a species. So all of this is in case the aliens from another star system found the craft. It would allow them to learn basic facts about our species. And I'm reminded, there was a comic shortly after these spacecraft did their thing, and they were well publicized. There was a comic, and it showed aliens who had come upon the Pioneer craft. And they're looking at this picture that we sent on the side of the craft, and these aliens are dressed in tuxedos, by the way. And one alien turns to the other and says, "They're just like us, except they don't wear clothes." It was a stupid comic, but I'll never forget it. But anyway, these plaques represented the first ever attempt to communicate with another species using pictograms and hardware that they might come upon. Now, Here they are on their way out of the solar system. We expect them to slow down. We know they're going to escape, but whatever speed they have, we expect them to slow down as they climb out of the sun's gravitational embrace. Now, since they have enough energy to escape entirely, they'll slow down, but never slow down to zero. Okay, that's fine. Here's the problem. The actual deceleration we measure is greater for each craft than what we calculate it should be after accounting for all the possible forces that could slow down the craft. That is the Pioneer anomaly. The effect is small, but it's persistent, and every attempt to understand its cause has failed. The effect became measurable about 8 years into the journey, but it was not studied in detail until about 1994. Now, we haven't communicated with the Pioneer craft since 2003. They're too far away now for signals to be exchanged. But we have data over a 23-year period from 1980 right on up through 2003. And that baseline of data continues to be studied. Now, consider, we've never before measured the force of gravity in the solar system with such precision over such distances for such a long period of time. So this constitutes a new experimental frontier. In physics, if you perform an experiment that's never been performed before, you almost expect something new to show up. You expect it because no one has done it before. It's looking in a place you had never had the occasion to look to understand the behavior of nature. All right, so what's at cause here? Is the sun misbehaving? First, you blame the engineers. That's what I would do. Blame the engineers. It's like, look, have you looked at all the possible onboard sources of what could interfere with the acceleration of this craft, okay? Have you looked at any possible sort of outgassing of fuel cells or fuel tanks? Or double check, triple check. Bring in the designer of the craft. Do you have a model of it here? Let's check that, okay? All of this has been done. All of this has been done. And all those sources of errors have been removed. We're pretty sure. Okay, so we ask ourselves, has this experiment found the limits of our current theories of gravity and motion? Or is there still some engineering problem that even the designers of the craft have not figured out yet? What we know is that this problem exists for both Pioneers, and they're not headed in the same direction. They're at like 90-degree angles to one another. They both have this extra deceleration. The Pioneer anomaly remains unsolved to this day. Do we know if it'll ever be solved? Because there's not another experiment right now ready to double check it. We're kind of stuck with these data for now. But I can tell you, if it never gets solved, and it is an anomaly, this is a piece of information that we're going to have to hold on to, not dust it under the rug, not just keep blaming the engineers. At some point, you have to blame nature. And when you get enough of those occasions where nature is misbehaving, you know it's time to come up with a new theory of the universe. And that might just be what awaits us. You know, 85% of all the gravity we measure in the universe comes from a source about which we know nothing. We call it dark matter. But since we're fundamentally clueless, we don't know what it is, okay? The dark matter is just a placeholder name We could easily have just called it Fred, all right? In both cases, we don't know what it is that's causing it, all right? We have no idea. Dark matter was discovered in 1933. It's been around for a while. It was discovered by an irascible astrophysicist named Fritz Zwicky. He was Swiss-born, but spent most of his professional life in America, in fact, at Caltech in Pasadena, California. What he did was he studied a large cluster of galaxies, happens to be called the Coma cluster. It has 1,000 galaxies in it. Whole galaxy. A galaxy has itself billions of stars, so this is a massive structure in the universe. And all these galaxies are bound together by their mutual gravity. And what he found is that the speed that these galaxies are moving within the cluster is faster than the collective gravity of each galaxy can sustain. In other words, at the speeds he found them moving, the galaxies should have flown apart from one another long ago. But they're not. They're bound together. They're still bound together. They didn't fly apart. He proposed that there's some missing mass that must lurk somewhere within the cluster whose extra gravity he was tracking. Now, this result turned out to be true for every single cluster ever measured ever since. Back then it was known as the missing mass problem. Today, we call it the dark matter problem. Let's fast forward. 1976. Carnegie astrophysicist Vera Rubin. She was studying the rotation of spiral galaxies. We're a spiral galaxy, the Milky Way. And what she found is that they were rotating faster than the known mass within the galaxy should allow. Dark matter, it turned out, was not a problem unique to galaxy clusters. It was a problem that revealed itself even within galaxies themselves. Could it be dark clouds, black holes, dark planets, anything dark? No, 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 and no. If it has substance, then it cannot be made of anything familiar. Familiar materials, they absorb, reflect, refract, and otherwise interact with light and other materials. But this stuff doesn't interact with anything at all, not even itself. It only reveals itself to us through its gravity. It is a fundamentally different thing going on than any possible measurements that our own familiar materials would reveal. So, you could ask, could it be an undiscovered family of particles that barely interact with our kind of particles? Sure, why not? In fact, that's the odds-on favorite scenario. And top particle physicists today are working on that. Could it be a failure in our concept of gravity? In other words, do we need a new theory of gravity to account for it? Unlikely, but we've got top gravity theorists that are working on that one too. They call it MOND, Modified Newtonian Dynamics. Seems like whatever is your specialty, you think the solution resides within your expertise. It reminds me of the old adage, if we were hammers, would the dark matter problem look like a nail? You know what my favorite possibility is? Maybe the dark matter is the ordinary matter of an 85% more massive parallel universe influencing ours by gravity leakage from one universe to another. I like that one. If so, it would be the first evidence of other universes. And yet, the evidence was there all along. You know, dark matter is the longest standing problem in modern astrophysics, and it persists to this day. As if one profound mystery of the universe is not enough. Recently, dark matter was joined by dark energy as one of the most profound sources of ignorance the astrophysicist faces today. In the late 1990s, teams of researchers led by Saul Perlmutter, Brian Schmidt, and Adam Rees discovered that the expanding universe, itself discovered by Edwin Hubble in the 1920s, was accelerating. That turned out to be a Nobel Prize-winning measurement. This force that's making it accelerate, we call it dark energy. But since we don't actually know what it is, we could just as easily call it Barney. All right, that's what I want. Dark matter I'll call Fred, dark energy Barney. It doesn't matter because they're just placeholder words to accommodate our ignorance. You don't want to read too much into those words. So, here's how it works. If the collective gravity of all the galaxies in the universe were all there was, then the expansion of the universe should be slowing down, not speeding up, because gravity is an attractive force, resisting the expansion. What we found is that there's a mysterious pressure operating in the vacuum of space, and it's combating the gravity and winning. We don't know its origin. We don't know what it is. We're not even sure of its long-term effects. Turns out, Albert Einstein, after he published his new theory of gravity in 1916, that's, of course, the general theory of relativity, he noticed that it predicted a universe that should either be contracting or expanding. Now, that's odd. How could everything you know, how could the universe do anything if it is everything? This was a profound scientific and philosophical dilemma. Unthinkable concept. And if it's expanding or contracting, compared with what? And so Einstein added a mathematically legitimate term to his equations. That term allowed him to stabilize the collapsing influence of gravity in a way to hold up the universe against its wishes. And that way he could keep the universe the same size, whatever size that was. Within just a few years, however, after Edwin Hubble showed that the universe was indeed expanding, Einstein rapidly withdrew the stabilizing term from his equation. You know what he called it? He called the introduction of that term the greatest blunder of my life. He knew, or he felt deep inside, that that term could not be anything physical. There's nothing in the universe that repels matter. Not on large scale. A magnet can do it, but on large scales, there's no known thing that could repel matter. So this term that he added to his equation, he was very uncomfortable about that. That's what left him to call it the greatest blunder of my life. Turns out, the measurement and existence of dark energy is precisely that term in his equations. What that term in his equations do is exactly what we see dark energy doing in the cosmos. So, in fact, Einstein's greatest blunder was saying that the inclusion of that anti-gravity term was his greatest blunder. Isn't it great to be so smart that you're right even when you're wrong? So, here's what you do. You take the energy contained in what we call dark energy, and it's 70% of all that drives the universe. Include with that percentage the dark matter, and we are driven to the humble, mind-blowing conclusion that 96% of all that is the universe is not anything we even remotely understand. 96%. And that all of our laws of physics, everything we know, love, interact with, and understand, or even can predict anything about the future, that falls into the 4% that remains. Now, Actually, it gets worse. Our most successful theory of the universe, quantum physics, allows you to calculate what you might expect to be the energy contained in the vacuum of space. We can do that calculation. It allows it. It predicts that there should be energy there. All right? We do the calculation. Quantum physics, it's never been wrong. It's our best understanding going. When you do that calculation, the answer you get does not match reality. The answer you get is off by a factor of 10 to the 20th power. That's a 1 followed by 120 zeros. Now, that's just embarrassing. I'm sorry. All right? We put forth our best theory to our biggest problem, and it gets us nowhere. In fact, it is the biggest mismatch between theory and observation that there ever was in the history of science. That's our state. That's our state of the science today. So, we are not only ignorant, our best theories in the universe can't guide us. So, I think that means we're driving blind. If you add together sort of the three kinds of things that occupy the universe, the familiar matter, that's what we're made of and what our telescopes detect. The dark matter, that's the source of 85% of all the gravity we see in the universe, and we don't know what's causing it. And the dark energy, the stuff that's making us accelerate against the wishes of gravity. Each one of those components creates a curvature of the fabric of space and time, just as prescribed by Einstein's general theory of relativity. If you add those curvatures together, what you find is that they create a universe that is perfectly flat. Flat. Now, that's not the only shape the universe could have had. The universe could have negative curvature, and if it did, that would have we would have a saddle shape. And a negatively curved universe has a net positive energy. The universe is neither a spherical shape, the shape of a ball. That would be positive curvature, having net negative energy. Now, another way to get insight into this is to think about the energy of orbits. An object in orbit is gravitationally bound to what it circles. And bound orbits have negative gravitational energy. That's how we describe this system. Increase the elongation of the orbit by pumping energy, giving more speed to the object, and the circle distorts and becomes an ellipse. Give it even more speed, the ellipse gets more and more elongated. There's just the right amount of energy, just the right amount of extra speed you can give this object so that it goes so far away it never circles back. In fact, it escapes to infinity. At that point, that object and the system and the orbiting object and the object around which it formerly turned has zero total gravitational energy. And that path is formally called a parabola. Give the object even more energy, then it gets to infinity and keeps going. That has net positive energy, and we call that trajectory a hyperbola. Now, you've actually seen these shapes before at home. Take a flashlight. All flashlights have a cone of light that emerges from them. If you take it and aim it straight at a wall, it'll make a perfect circle. Take it and tip the angle just a bit. That circle distorts and you get an ellipse. Tip the flashlight so it's parallel to the wall, and you'll see the shape on the wall and it'll take the form of a parabola. Angle it a little more, it opens up even further and you get a hyperbola. Try that at home. So, these are what we call conic sections, intersections of a cone of light. And they relate to orbits and they relate to the energy that those objects have. Now, if your space-time is flat, just as if your orbit were a parabola, it means The universe, the entire universe, possesses zero net total energy. Think about that. If the shape of the universe were anything else, positively curved or negatively curved, it would not have zero energy. It would have negative energy or positive energy. We have zero net total energy. Now you wonder, is that good or bad? There's a silver lining to this. What it means is that you can create the entire universe out of nothing because nothing has no net energy associated with it. Had the universe been endowed with either negative or positive energy, we'd be forced to confront the questions of what was the original source of energy that begat the universe. And if it had some amount of energy, why is it that amount and not some other amount? The fact that we live in a zero energy universe bypasses that line of questioning. And does it leave us content in our emptiness? Perhaps. But we're no less enlightened by the ignorance that led to it. You know, while all this is going on in the universe, there's something that I think about often, and it's the fact that the Milky Way, the galaxy in which we live, is actually on a collision course with the nearest large galaxy to us, the Andromeda Galaxy. In fact, pictures of the Andromeda Galaxy are what we use to show what our Milky Way might look like from the outside. Because it's kind of hard to see what we look like since we're in it. All right, we see stars right in front of our noses, we see these gas clouds, but the grand design spiral pattern that spiral galaxies are so proud of, we see that in the Andromeda, we infer that for us. Okay, so we have several 100 billion stars in our midst. So does the Andromeda Galaxy. Andromeda Galaxy is about 2 million light years away, and we're on our way towards each other. It is a collision impending. It will be a train wreck. Think about it. Here's every star in our galaxy attracting every other star orbiting the center of our galaxy where there's a supermassive black hole. That system is falling towards another system that also has several 100 billion stars all attracting each other. As they get closer and closer and closer, just imagine this, all right? Every star feels every other star's gravity. And as they merge, with the motions combined with it, stars get flung hither and yon. There'll be stars that'll be kicked out of both systems and will become lost to intergalactic space. The two black holes, we've got a black hole, they've got a black hole. They're going to be making a beeline for each other. They will feel each other's effects, okay? And if we're not in a direct collision course, even if we're to the side of each other, we will go into orbit around each other. And those black holes will eventually coalesce and make one bigger than either one started out to be. Eventually, our two galaxies will become one, a big, fat, double galaxy. And given enough time, you would have no trace that we started out as two separate systems, separated by 2 million years. 2 million light years, that is. Oh, by the way, a light year is about 5.8 trillion miles. See, that's why we just call them light years. It's easier. All right, here's what's interesting about that collision. These two galaxies, we think galaxies have collided all the time. We see images of galaxies that are badly disturbed. And in the early days of this exercise, we just thought they were irregular galaxies. In fact, that was an official classification for them. Until there was an astronomer who said, wait a minute, this was his exact words, a wrecked Lexus is not a new kind of car. It's just a wrecked Lexus. So if you have a galaxy that's badly disturbed looking, Maybe it was an ordinary galaxy that's in the middle of a collision. So we looked around the universe and we found galaxies in all stages of collapse towards each other. You can practically make a timeline of what our collision with Andromeda will look like based on the collection of all the galaxies we have out there in the universe that are in the act of colliding with each other. And so, this is in our future. The problem is, we will collide with Andromeda after our sun dies. After the sun around which we orbit expands to become a red giant and engulfs the orbit of the Earth, rendering us a charred ember soon to become vaporized. So we need to find a way to move to another planet or another star system to watch this happen. But then when we watch it happen, if a star comes too close, you can have a flyby looting of the planets that belong to one star get stolen by another because stars will be flying back and forth. So, it'll be an exciting time for Earth when that happens. Or it'll be an exciting time for any civilizations alive to watch it. What we don't know is whether Earth will survive that. Will we be among those flung into intergalactic space? Will we fall towards the super duper massive black hole that now occupies its center? Or will we find a new home around a new star that is perhaps just born, giving us a new lease on life for the apocalyptic civilization that follows ours? I got one for you. What happens when the theory of the large meets the theory of the small? In this case, what am I talking about? The theory of the large, Einstein's general theory of relativity. That's our complete understanding of cosmology. It alerts us to the nature of the space-time continuum that spans the universe. The theory of the small, of course, it's quantum physics. Quantum physics. These two theories apply in their own regimes. Quantum physics, the theory of the small. General relativity, the theory of the large. Yet they are fundamentally incompatible. Quantum theory requires that space and time be quantized. That's what quantum theory means. That space and time are not infinitely divisible into a smooth continuum. It actually breaks up into pieces, and you can't get pieces any smaller than that. Meanwhile, general relativity requires that space and time be smooth. Like I said, they both work in their own regimes, but you can ask the question, what happens if they have to meet each other? What happens if they have to operate in the same place at the same time? Just such a situation existed in the very early times of the universe. In the early times, the universe, as we know, is expanding. That means yesterday it was smaller than it is today. You go back early enough, there's a point where the entire universe was in the same place at the same time, occupying an extremely small volume. A volume small enough that it rivals the scale over which quantum physics applies. The entire universe within the size of an atom. Under those conditions, what do you have? You have like a shotgun marriage between these two incompatible theories. Something's got to give, because the large becomes the small. Well, the effort to merge these two theories, these two great understandings of our universe, comprises part of what the work that string theorists do. Among other things that they're up to, that's a big part of it. Can you merge these two great theories of the universe? And what this spawns are ideas, really freaky ideas like quantum foam, where the fabric of space and time is so tightly curved onto itself that space-time is less like a smoothly curved fabric and more like the froth on a latte. In this state of matter and of energy, quantum fluctuations, which are a normal part of quantum physics, they can spawn entire universes. Since a universe is the size of an atom, a quantum fluctuation births an entire universe, each with slightly varying laws of physics from each other. And all this unfolds in dimensions higher than our own. Now, not all universes will survive the laws of physics they've chosen for themselves. Some will recollapse before stars are born. Others will expand so fast that matter never has the chance to coalesce into galaxies and stars. And still others might succumb to laws where no matter is stable at all. We're in the one that allowed some of the matter within it to achieve consciousness and to contemplate its very existence. If quantum fluctuations give rise to multiple universes from within that quantum foam, then what do we call this entity? Multiple universes being born? The multiverse, of course. The multiverse. I've given some of the theoretical arguments in favor of it, but there's also historical, philosophical arguments in its favor as well. Let's go back in time. There was a day when Earth, pre-scientific era, there was a day when Earth was imagined to be all there was. Everything else orbited around us. So Earth was singular, unique, large, and important. We would later learn that Earth is just one of many other planets. The planets that we saw in the night sky were not something smaller and lesser than we are. In fact, among planets, we're actually quite small. Jupiter has storm systems in its atmosphere bigger than the entire planet Earth. So that'll set you straight right quick once you make those comparisons. So we learn that there's not just one Earth, there are many planets in orbit around the one sun. Of course, our sun is special, it's big and it's bright. And look at those stars in the night sky, they're just small and dim. No, they're just far away. In fact, the sun is not even unusual among stars. It's not the biggest or the smallest or the brightest or the dimmest. It's kind of average, actually. So we learned that our sun is just one of countless other suns, evolving in our mindset from a time when we imagined the sun to be unique in the galaxy. How about the galaxy? The Milky Way. We see the band of light in the night sky. Surely that's unique, yeah. We're the one galaxy that comprises the universe. Nope. As we've said many times, Hubble showed that our Milky Way galaxy is but one of countless billions of galaxies in the universe. The universe. How about the universe? Surely there's only one of those. There we go again. You want the universe to be singular? Nothing before this has ever been singular, in spite of our urges to require that to be true for them. In fact, as far as we can tell, there's nothing in the universe that comes in ones. Perhaps not even the universe itself. So, this actually gives us a place to stand regarding that perennial question, what was around before the universe began? Perhaps we began as a single quantum fluctuation among countless others in a hyperdimensional multiverse. But, of course, that just shifts the question to a new paradigm. What was around before the multiverse? Or, better yet, if indeed the universe never makes anything in ones, not even the universe itself, then perhaps the multiverse from which we are born is part of a system of multiverses. And that part of a system of those, and so forth. Given that we started all this thinking that Earth was something special in the center of the universe, it can be quite a blow to one's ego. But only if your ego started at the beginning of the day much larger than the cosmos can justify. So we take this fact and use the trend line in the history of our discoveries to try to never have an unjustifiably large ego. Because just wait a few decades, at most, we're going to find something about the universe that puts us in our place. And such is the continued progress of our discoveries about our place in the universe. In the early universe, we know that everything was packed into a small space and the temperature was very high. And when you have a high temperature, the world around you behaves very differently from what goes on here on Earth. There's an equation that matters that drives everything. And we've learned this equation in elementary school. It is, of course, E equals mc squared. Hold the c squared aside for a moment. That's just a constant, and it happens to be the speed of light. What matters in that equation is that energy is recognized to be equivalent to matter. You can convert them back and forth at will, provided you have enough energy to pull it off. And when you do so, you can create particles out of energy fields and energy fields out of particles. This was going on incessantly in the early universe because it was just that hot. Now, how does that work? Well, light, anywhere you see it, typically visible light, doesn't have enough energy in it to make particles. That's why E equals mc squared does not manifest itself in any obvious way in everyday life. But if I was instead being bathed not with visible light, but with high energy X-rays or gamma rays, that's light too. X-rays and gamma rays, that's a high energy version of visible light, okay? That kind of light has enough energy to spawn spontaneously. It can create particles, electrons, for example. Now, there's a symmetry to this. Symmetry is a beautiful concept in the universe. What we have found is that if you take light and make matter out of it, the energy from light, and turn it into matter, it makes pairs of particles every time. If you take a high energy X-ray, it'll make an electron and the antimatter counterpart to the electron, the positron. It'll spontaneously create them and they'll fly apart in opposite directions. If you bring those two particles back together, they annihilate and become energy once again. This is E equals mc squared manifested. And it does this all the time in the early universe, and it's a kind of an equilibrium particle soup that went on back then. All right, so here's what happened. Every time you make particles, they come in pairs. Every time they annihilate, they disappear completely. If that's all that went on in the early universe as we expanded and cooled, there'd be a day where every matter-antimatter particle annihilated, it would create light. That light would cool, wouldn't have enough energy to make particles again, and the entire universe would be just filled with light and no matter in it at all, because everything was symmetric. All matter got annihilated with its antimatter counterpart. All particles got created in pairs. So if symmetry, which we know and love, that drives so much of the laws of the universe, if symmetry were preserved, we wouldn't be here to talk about it. So something must have happened in the early universe, and we call it symmetry breaking. Nature disobeyed its own laws. At some point, a high energy beam of light created a matter particle without the antimatter particle pair. That's a breaking of the symmetry. And we know how often this must have happened. 1 in 100 million of these phenomena gave us a matter particle and no antimatter counterpart. This matter particle now will live forever because it's got nobody to annihilate with. All the others annihilate. So in fact, the universe that we see, know, and love today is the consequence of broken symmetry in the very early universe, shortly after the Big Bang. It's a mystery. We don't know why it happened. We try to produce it in the lab. Everything we do in the lab is symmetric. Anytime we create particles in the lab, it's a matter-antimatter particle pair. Every time we put them back together, we get light. So something happened in the early universe. We call it a phase transition. You're familiar with phase transitions in everyday life. Water goes to ice. The fundamental properties of it changes across that border, the freezing point. Water can go to steam. That's another phase transition. So when we think of periods in the early universe where things were really different on one side of a transition from the other, we call that a phase transition. And in that particular case, it was the breaking of the symmetry of the matter and antimatter in the cosmos. So I bet you never thought that you would embrace and love the fact that while we have antimatter, there's a point where, unless nature breaks its own rules, we wouldn't even be here to contemplate the fact that it broke its own rules. As far as we know, nothing can travel faster than the speed of light in a vacuum. Period. Okay? It's not like we haven't wanted to make that happen. It's not like we haven't looked around the universe to see if we can find something that violates that rule. We have. We've looked hard. We've never found anything to violate that rule. Not only that, it is a fundamental tenet to Einstein's theories of relativity. Okay? So what that says is this speed of light rule is not a limitation of technology. It's a basic fundamental feature of the universe. Now, you might be thinking, look, you guys once said we'll never be able to fly with heavier than air hardware, or you will never break the sound barrier. We'll never go faster than light. You know, this is where I hear this all the time. Except these are fundamentally different statements. What's different about them is the people who said we will never fly fast, that we'll never fly. Well, okay, when they said that, surely there were birds flying overhead. Surely. So it's not like flying is impossible. You just haven't figured out how to do it yet. All right? That should have been obvious to that person. That statement should have been, we have not yet figured out how to fly. And birds are heavier than air and they manage it just fine. And this thing will never travel faster than sound, the sound barrier. Well, we had rifles at the time people were saying that where the bullet coming out of the rifle traveled faster than sound. We had the bullwhip. When you flick a bullwhip, the very tip of the whip, the reason why it makes that cracking sound, that's like a mini sonic boom. It is traveling faster than sound. We had things that travel faster than sound. Just because you couldn't figure out how to make an airplane do it, that's not my fault. Not the fault of the universe. So those two claims are fundamentally different from the assertion that we will never go faster than light. Doesn't mean we haven't thought about it. In fact, there's a hypothetical particle that was invented just to accommodate what would happen if we went faster than light. And they're called tachyons, from the Greek root of that word meaning speed. A tachometer has the same root as the word tachyon. These are hypothetical particles. We've never found one, but we imagine what would it be like if particles existed faster than light? Well, it turns out Einstein's relativity tells us you can't accelerate any material object to reach the speed of light, but if you put in an object that exists faster than light, you can still run through all the equations, and the equations don't mind. But some interesting properties emerge. For tachyons, what do you get? They exist faster than light. It will require an infinite amount of energy to slow them down to the speed of light. So in fact, they can never reach the speed of light. And because they're going faster than the speed of light, they live backwards through time. How would you ever detect such a thing? Well, here's what you do. You find out what kind of interaction your tachyon would have with particles that exist in your present. So as they go backwards in time, they have to share your present, even if for only an instant. So we looked at what energies the tachyon would have, what particle interactions might be favored for a tachyon. We've looked for them, we've never found it. And so to this day, a tachyon remains an intellectual curiosity that itself does not violate any known laws of physics because it's not crossing the speed of light barrier. It's existing faster than it. But the day we find a particle faster than light, we'd bet pretty sure that it'll have all the properties that I just described, which would make it one of the coolest particles ever discovered. Now, there are other ways to go faster than light. You can cheat in a legal way. For example, on Star Trek, everybody's favorite sci-fi series from the 1960s, Star Trek, what did they have? They had warp drives. Warp drives, what did that do? Well, here's your galaxy right there, and they're on one side of the galaxy and they want to get to the other. So what do? They turn on the warp drives, and that takes the space-time continuum and bends it. And now here's where they are, and here's where they want to go. They just take a little gap through the fabric of space-time, unwarp the galaxy, and there they are. They cross the 100,000 light-year diameter galaxy during the TV commercial. Works every time. So that's legitimate in the sense that we know space and time can curve. And if you can control that curvature, you can get to a place much faster than a light beam would have taken. In time, much less time than it would have taken a light beam to traverse that same journey. And so that's we allow that. That's a cool, I want warp drives that can do that. That would be really cool. But not only that, this little path that they took to cut from one part of their space-time to another, we have a term for that as well. It's called a wormhole. That is a portal in the space-time continuum that takes you from one part of the universe to another. And the more energy you have, the more you can curve major sections of the universe to traverse great distances. And I assert that if we're ever going to travel the stars, if we're ever going to cross the galaxy or visit another galaxy, it's going to have to be in some kind of way that exploits wormholes and the curving of the fabric of space and time. It's going to have to, because our fastest spaceships, if you hop a ride on them today, would take you 50,000 years to reach the nearest star to the sun. And the nearest star to the sun is sitting on our nose compared with the scale of the galaxy. So, watch that space. Look for the invention of a warp drive, because I'm going to be on that first spaceship that has it. You ever wonder what the long-term fate of the universe is? We think we know enough of the laws of physics and the behavior of stars and galaxies to actually have some insight into what that looks like. Because stars don't burn forever. Stars will not continue to be made forever. There's a winding down of the cosmic clock that we know enough physics to be able to track. So, let's go forward in time. One of my favorite moments will take place in about 7 billion years. We chatted about it a few lectures ago, and that was the impending collision between the Milky Way galaxy and Andromeda. Galaxies all around the universe, if they are within each other's gravitational embrace, they will ultimately collide. This is the very distant future. Some galaxies look like they're on a stable orbit around each other, but there's an erosion of that orbital energy that is happening with any two orbiting objects. They will eventually collide and merge. Okay, how about the gas clouds that are generating stars? Eventually, we're going to run out of gas. Our galaxy, about, I don't know, 10, 20, 30% of its mass is in gas, and it is cranking out stars. There's some nearby fascinating regions of star formation in the sky tonight. Okay? So we keep making stars, so everything feels like it's in equilibrium. Stars die, other stars are born. The problem is, for every star that's born out of a gas cloud, most of those that are born don't return their gas into space. It gets locked up. And so every time you make a star, you are draining the supply of gas clouds. The day will come when there's no gas left. All the gas supply is exhausted, and the era of birthing stars will have stopped. Now, that is 1 trillion years from now. Don't hold your breath. It's a while. Don't worry about that. However, right about then, something else will happen. Remember this dark energy I've been telling you about that's forcing the universe to accelerate? You got to realize that that acceleration is catastrophic. It will take every galaxy in the expanding universe, and in a not very much time from now, it will accelerate them beyond our horizon. Now, let's back up for a minute. Let's back up. Before Edwin Hubble showed that the fuzzy spiral things in our night sky were not just fuzzy spiral gas clouds among the stars, they were entire other galaxies beyond the stars of our Milky Way. But before that moment, we would sit out under the stars, look up, and imagine that those stars was the entire universe. That was the state of mind at the time. It was not until Hubble where we learned that there are other galaxies out there. It's an interesting transition in our understanding of our place in the universe. Now, what effect dark energy has in the rapid expansion of the universe is that all the galaxies of the night sky recede so fast that they go beyond our horizon. What is a horizon in the universe? It's just kind of like our horizon here on Earth. You put a ship out to sea, and it looks out to the horizon, and is that the edge of the Earth? No, you know better. You can travel in that direction, and you see more Earth come into view. But at any given instant, there is an edge beyond which you cannot see. And if a ship goes across that edge, it is gone from your sight. That concept of a horizon at sea has much in common with our three-dimensional horizon in the universe. And so, here's what will happen. As these galaxies accelerate beyond our horizon, there's an important chapter in the history of the universe that will get erased, torn from the pages of cosmic truths. Without galaxies in our night sky, any post-apocalyptic Earth civilization will know nothing of the cosmic history of the universe. It'll be the end of cosmology. Everything we know about the beginning of the universe comes from studying galaxies, not from stars, galaxies. And what will happen at about that time in the future of the universe is that anyone on Earth or in our galaxy at all who looks up at the night sky, that night sky will resemble the pre-Hubble night sky. Except the difference is, back then, they only thought the stars in the night sky was their entire known universe. Whereas in our future, the stars of our night sky in our own galaxy will be the entire known universe. There'll be no galaxies available to us. That's an interesting chapter in our lives. Because if we're trying to be scientists, if we're trying to be astrophysicists, if we're trying to be cosmologists in that time, there's a chapter missing. There's a piece of the universe not available to us. There simply would be no cosmology at all. Get back to that in a minute. Let's continue to evolve the universe. All right. Eventually, without any stars to do the replacing, the stars end up burning out. One by one, they turn off in the night sky. The sky starts getting dark. Eventually, we theorize that the proton will decay. The very structure of matter itself will decay into lesser, lighter particles. That's bad. That's bad for matter, okay? That's way in the future. Now we're talking at least 10 to the 33 years. That's huge. I'm talking about the very distant universe here, okay? Very distant. I'm self-aware of this. All right. You keep going far into the future, all the orbits of galaxies decay. They spiral down ever so slowly, but they'll eventually get there and pile onto the central black hole that lurks in the center of every single galaxy. So every galaxy loses its stars. The remnant cores of each star that burned out eventually spiral down into their black holes, and you have this sea of black holes in the universe. Those black holes eventually evaporate using Hawking radiation. They evaporate. That takes 10 to the 100 years. That's a Google years. Google spelled G-O-O-G-O-L. That's the original spelling of Google. Got nothing to do with the company. The mathematicians had that word first. So, what is going on? The black holes evaporate, stars are gone, the universe is dark, and as it expands, it continues to cool, and the universe plunges towards absolute zero. During this expansion, as it cools eternally. What this tells us is that no, the universe will not end in fire, but in ice. All right, now let's get back to my night sky that's missing galaxies. On the short list of what keeps me awake at night, I ask, is today a time in cosmic history where some chapters in the cosmological storybook have been previously removed? Today, I ask that. I know that in the future, we're not going to have cosmology because there'll be no galaxies. Is there something we don't have today, and I don't know we don't have it today? And I'm trying to figure out the universe, and I'm missing an important chapter. I'm missing the rule book. I'm missing the index. I'm missing the primer of how to figure out how the universe works. Because if we are victims of such a gap in the data on the universe, then we're surely just groping in the dark, delusionally thinking that we've been granted full access to the universe. We want data. We need data. We require data for us to deduce the correct operations of nature. And so I ask, is our ignorance that prevails today, that we're only 4% of the universe and the rest we're clueless about, is that state of ignorance the consequence of a missing chapter in cosmic history? Or is it just the next set of mysteries awaiting the birth of a new Newton or an Einstein? Or perish the thought, maybe in this particular case, the human intellect is insufficient to answer part of cultures that value deep thought, that actually have the luxury of time to invest in trying to deduce the nature of the known world. One of my favorite examples of this is Claudius Ptolemy. He was an Alexandrian astronomer and mathematician, and he was around at 2nd century AD. He came up with a coherent, complete understanding of the known universe. And he put it all in a book called Almagest. Almagest is actually Arabic for the greatest. Aptly named, I think. Now, his ideas happen to be wrong. He put the Earth in the middle of the known universe. That's the geocentric model of the cosmos. But when you think about it, that's what the world looks like. Everything orbits Earth. And does it feel like Earth is moving under your feet? No. So his model was what made common sense to everybody. But deep down inside, I think he was still didn't feel like he grasped it all. Because he would follow the movements of the planets in the night sky. They would slow down, stop, and then reverse, call it retrograde. This is complicated motion to try to explain. In his greatest work, he penned in the margin my favorite quote of all time. He said, "When I trace at my pleasure the windings to and fro of the heavenly bodies, I no longer touch earth with my feet. I stand in the presence of Zeus himself and take my fill of ambrosia." That's Claudius Ptolemy basking in what he understood about the universe, but was humble in his ignorance. Because deep in that quote was the recognition that I don't think he really believed he fully understood what was going on. Why else would he bask in the presence of Zeus? Well, it would be 1,400 years where people just accepted the geocentric model. Again, that's an era where experiments on ideas is not yet an understood thing to do. 1,400 years would go by. Nicholas Copernicus, 1543, on his deathbed, would propose the heliocentric model of the universe. He wasn't content with what the hoops Ptolemy had to jump through to account for what we saw. How else do you get planets to go forward and backwards and forward and backwards? Ptolemy had systems of multiple orbits on top of orbits called epicycles. Things orbiting nothing in space. In fact, the word orbit wasn't even quite defined back then. This was just movements. And Copernicus said there might be an easier way. Let's put the sun in the middle of the known universe, and if you do that, Earth becomes one of the planets. That's heretical. Copernicus waited to his deathbed before he published this, knowing the kind of retribution that would be exacted upon him in that period of Europe, the mid-16th century. Did not take kindly to heretics. So you can't kill him, he's already dead. So he puts out the heliocentric universe on his deathbed. It was right in every fundamental way, except he had the orbits as perfect circles. It would take a few years to iron that out. But what's important here is that the world embraced an idea that was wrong, but made sense. Wrong, but it made sense. That ought to tell us something. That not everything in the world that makes sense is correct. And if that's the case, then who are you? What of Ptolemy's Zeus? What of the reverence he's showing? If he actually understood it all, would Zeus have even shown up in his quote? And if you're prone to assert that God is the influence of all that we don't understand, because the hand of God is greater than anything your mind can comprehend, then what of God? Throughout history, the urge has been strong to, upon recognizing your area of ignorance in the universe, to assign the handiwork of God to those ideas, to those phenomena. If you feel that way about prevailing ignorance, then you're actually in pretty good company. Isaac Newton did just that in his most famous work, Principia Mathematica. The translation from the Latin is The Mathematical Principles of Natural Philosophy. That's the full-up title of that book, published in 1687, in which he discovered the laws of motion, the universal law of gravitation, and in it, it represents the fruits of his effort for having discovered calculus to solve some less to understand and decode the movement of objects in the solar system. And it's worked in every place we'd ever applied it. So why not be cocky about it and say it'll work even in places we have yet to imagine? These methods and tools are empowering our capacity to understand objects in the solar system. Okay, I'm with you on that. That Newton's laws, they're good. They're good. But let's see what happened. Over the centuries, careful timing of the movement of Mercury around the sun, that's the innermost planet. It orbits in an ellipse. It turns out the ellipse precesses around the sun. We've known this. This is not news, right? While Mercury is orbiting, the entire ellipse precesses ever so slightly. All right, we're fine. Turns out, when you calculate how quickly this should precess, and then you observe how fast it's precessing, those two numbers do not match. They differ from each other by, if you're angle fluent, 43 arc seconds per century. That's small, and it took a long time to establish that baseline of measurement to say that these two do not agree. All right, well, what's causing it? Nobody knew. But in 1859, riding high on his successes with the planet Neptune, Leverrier said, I got this. Look, I've been there before. How do you think I helped you find Neptune out there? There must be some other source of gravity we've yet to tally in our inventory of objects in the inner solar system. So he said, I got it. Maybe there's a belt of asteroids, a second asteroid belt in the solar system between Mercury and the sun. And the collective gravity, that's what's giving an extra tug on Mercury. Within a few years of that, there was an astronomer who made a measurement of a planet moving across the sun's surface, a planet that was not Mercury. Leverrier said, okay, I don't need the asteroid belt. It must be that object. In fact, I'll name it. I'll call it Vulcan. Awesome name for a planet. Anything that close to the sun, that's the name it has to have. That's the root of the word volcano. So that became the scapegoat for this extra tugging on Mercury to create that difference in the precession. Problem is, another person with a better telescope observing the sun at the same time as this other astronomer was making his measurements said, I saw nothing go across the sun. There must be something wrong with your measurements. And practically overnight, Vulcan disappeared from the data. It was a faulty measurement that had been reported. So now Leverrier was left with nothing to credit for the movement of Mercury. But maybe you can still get away with it. Maybe it's so close to the sun it's always lost in the glare. Plenty of people were happy with that explanation. And we went on saying, yep, it's Vulcan. Never found it. We don't know where it is, but surely it's there. Enter Albert Einstein. 1916. He publishes the general theory of relativity, the modern theory of gravity. In it, space and time is a fabric. Think of it as a deformable fabric. And gravity is not a force between two objects. Gravity is the shape of that fabric. And bodies move according to where that shape tells you to go. And when you factor in all the tenets of relativity, what we found is that Mercury was following the severely curved fabric of space and time in the vicinity of the extreme extremely significant and strong source of gravity that is the sun. In fact, Newton's laws do fail when you're that close to an extreme source of gravity. This shocked the world. And it's a reminder that here we were invoking Newton's laws. We were ready. We invoked Newton's laws to discover the planet Uranus. And in our cocky ways, we said, we're going to fix the Mercury problem the same way. Only to find out, no. Mercury required an entire new branch of physics to be invented, just to explain it. And so, yes, nature can be subtle. That is the beauty and the challenge that the modern scientist faces. You know, not all investigations of the universe involve pieces of the unknown. Occasionally, people are challenged to take it all in and come up with a coherent, complete understanding of the known universe. In fact, the people who get to do this are, of all the amazing things about the universe, I think two stand above all the rest. One of them is that we know so much about the universe. But another is that there's even more that we don't know. And what I want to focus on for this lecture is the inexplicable universe from a time gone by that is now explained. Human cultures have for a long time harbored scientific mysteries. In fact, in the pre-scientific era, that would be before Galileo, 400 years ago, before then, many of nature's most unknown mysteries were thought to be the work of divinity. Take, for example, epilepsy. There's someone writhing on the ground, your best friend, frothing at the mouth. If you're driven by Christian theology, your first thought is the person is possessed by the devil. That's the natural explanation for what's going on there, in the absence of any other knowledge about neurosynaptic processes. In another example, you could go out to the woods one morning, one damp, cool morning, and you'll find this circle of mushrooms. No one knew how they got there. You were there the day before, there was no trace of mushrooms. And now, there's a perfect circle of them. These were known as fairy circles. And people imagined sort of woodland nymphs, woodland fairies coming to have a jamboree, and these were their chairs. Little fairies, of course. These were their chairs, where they celebrated whatever were their rituals of the night. We would later learn that, of course, mushrooms they're not solo organic entities. They're, in fact, one spore can generate many, many mushrooms. And if a spore drops in one spot, it can work its way out and get ready for just when the conditions are right, just the right temperature, just the right humidity. And then they all pop up, equidistant from where that spore first dropped. So explanations came later to these phenomena. And of course, we know epilepsy is the result of random firing of the brain, uncontrolled firing, that leaves you helpless in the presence of a brain gone awry. So what we found is that things started to change in the rise of the experiment. If you go back in time to Aristotle's day, people imagined that you could just sit in a chair and just think about the universe. You didn't have to go out and test it. You just thought it up. Aristotle imagined that heavy things fell faster than light things. Of course, yes, a rock falls faster than a feather. The feather feels the air resistance on its way down. But take a heavy rock and a light rock, they'll actually fall together at the same rate. Aristotle, however, said that the heavy one will fall faster than the light one in direct proportion to its weight. This is patently false. And it would take Galileo 1,500 years later to demonstrate that this was the case. He describes the experiment of dropping two balls from the side of the Leaning Tower of Pisa. And they're both falling at exactly the same rate, hitting the ground at the same time. Of course, that would happen with a rock and a feather. You just have to evacuate the air from where you're doing the experiment. In fact, that was indeed done, that very experiment, on the surface of the moon. So what I want to do for this lecture is focus on several stunning examples of profound mysteries that plagued the deepest thinkers of their day, but ultimately got explained. There was a single biggest scientific mystery of the 19th century. It preoccupied the greatest minds of that period, and what it related to was at the core of our understanding of space itself. What's behind it? Well, we know that waves require some kind of material medium through which to travel. And the best and most common example of a wave is sound. Sound moves through air, but if you take away the air, it cannot propagate. You may have remembered this experiment. It might have happened in your high school science class. You have a ringing bell, and you enclose that bell in a glass container. And you start pumping the air out of that glass container, and the ringing bell gets dimmer and dimmer and dimmer to hear. And at some point, you don't hear it at all, yet you still see it clanging away. That's evidence that sound cannot pass through the vacuum that you just created. Well, if light is a wave, then it too must require some kind of medium through which to travel. Here's the problem. Empty space is a vacuum, and we know that light reaches us from empty space. The moon is in space, the sun is in space, the stars are out in space, and there's a vacuum between us. 20th century science and onward entered a time where, in fact, in order to understand the universe, at least some of the time, you had to abandon your senses. Next up is the discovery of the planet Neptune. But first, let's go back in time to 1781 for the discovery of the planet Uranus by Sir William Herschel. He's the only one in town with the big telescopes during that day. And he found Uranus by accident, actually. He thought he had found a comet. Nothing else would have moved against the background stars except comets. It was inconceivable to him that he could have discovered a planet because nobody had ever discovered a planet before. Mercury, Venus, Mars, Jupiter, and Saturn in the sky are visible to anyone who looks up. They don't require a telescope. He was in denial for so long. He thought he had seen a comet, and he would say things like, "Curious comet this is. It refuses to show any fuzz, as any good comet ought to." Fact is, the man discovered Uranus. So here's the question. Does Newton's law of gravity apply that far out in the solar system? Newton's laws of gravity had been tested between the Earth and the Moon and all the inner planets and the Sun, and it was working. It was good. It was powerful. It was predictive. And so here we are at the outer reaches of the solar system. Well, let's test that. We're in the era of testing ideas. So let's wait 70 years. And over those 70 years, we're going to get data on where Uranus is in its orbit. Okay? How long does it take Uranus to complete an orbit? 84 years. So 70 years is most of 84. So you're doing good. You've got a lot of good data to compare. You say, where should Uranus be according to Newton's laws? And where do I measure it to be in the solar system? Is there a difference or not? If it's bang on, we're good. Newton's laws work out there, we're fine. What we found is that they didn't match. Do we throw out Newton's laws? You know, they're pretty good. They're working for us. No one really wanted to abandon them. If you don't abandon them, what are your options? Maybe there's another source of gravity you haven't reconciled with your efforts. All the other sources of gravity you factored in, you're missing one. And if you included it, maybe that would account for why it looks like Uranus is behaving badly. So, thus began the hunt. British mathematician and astronomer John Couch Adams, he was a specialist in celestial mechanics. This is the physics and the mathematics of the movement of bodies in the solar system. And a French mathematician, Urbain Jean-Joseph Leverrier, did exactly the same thing. And it's a tricky problem because typically you would use Newton's laws by saying, here's a body and here's a body, calculate the force between them. This is different. Here we have the force between them, but there's some body out there and we don't know where it is or how much mass it has. So it's an inversion problem with Newton's laws. You have to calculate things backwards from what you're accustomed to, and that takes pages and pages of data and calculations to get it right. So each of these brilliant mathematicians predict where and when you should find the perturbing object that was out there. It happened to be Leverrier, who was friends with Johann Gottfried Galle in the Berlin Observatory. He was an astronomer there. Leverrier assisted him, told him, here's where you should look, and here's when you should look. Johann Galle looked where and when Leverrier said he should find it. Within 1 degree of the predicted position, he found a new planet. The planet to be known as Neptune. This was a triumph of mathematics and the laws of physics. It was a case where you weren't using the past history of rhythms to predict the next event. You do that with like the phases of the moon and eclipses and things where you have a good record of what it was doing before. This was a case where there was no previous record. A planet was predicted and discovered simply by laws of physics and understanding the operations of nature. This would shape the expectations of all subsequent discoveries in the solar system because Newton's laws were working. And next, we would apply those very same laws to the orbit of Mercury. Nature can be subtle. I don't know if that's a good thing or a bad thing just yet, but it's certainly true. I'll give you some examples. Take Newton's laws. Newton's laws of motion and gravity are powerful tools that enable. So it was hypothesized that no, there's not air out there. There's got to be something, some substance, some medium that light requires for it to propagate. And we gave it a name. My science ancestors of that period, they gave it a name. It was called the ether. The ether. We ought to be able to measure it. 2 scientists came along. This is in the late 1800s. The physicist Albert Michelson and the chemist Edward Morley. 2 American scientists. And they got together, collaborated, and perfected a new kind of tool called the interferometer. It's a special instrument that allows you to measure with high precision distances and speeds. And so in 1897, they conducted what came to be known as the Michelson-Morley experiment. So here's what they did. They said, all right, here's Earth. I'm going to measure the speed of light with the movement of Earth around the sun. Then I'm going to measure the speed of light against the movement of Earth around the sun. And if there is an ether out there, I ought to be able to show that the light added to Earth's movement, and I measure the speed of that, I'll get the speed of light plus the speed of the Earth. And coming back the other way, if I make that measurement, I'll get the speed of light minus the speed of the Earth. That makes complete sense. Of course it does. If you're riding in a train, back then it would have been a train, not a car. You're riding in a train that's going 30 miles an hour and you send something forward 10 miles an hour, you add them, that object is moving 30 plus 10, 40 miles an hour relative to the ground. Come back the other way and you throw it out the back end of the train, that speed will be 30 minus 10, 20 miles an hour relative to the ground. It's that simple. That's all they were trying to do with the speed of light. Upon conducting this experiment, what they found is that the speed of light was the same no matter where they made the measurement. And this was astonishing. It was the greatest null result ever found for a scientific experiment. A null result is you expect to find some kind of measurement and you don't. Usually those experiments are like not interesting, but this was the most interesting null experiment ever conducted. And so what do? Everyone knew there had to be an ether. So there were a couple of guys who said, all right, we can solve this. There's a fellow named Lorentz and another one named Fitzgerald. And they got together and said, we know what's going on because there's got to be an ether. Your measuring tools have contracted in the direction of motion. They've physically contracted to fool you into thinking that you're getting the same speed of light. That must be going on. Now, just think about that. So embedded were they in the existence of the ether. The ether, this traditional concept that a wave requires a medium, that they would not even entertain the possibility that there was no such thing as an ether. They would rather assert that something odd was happening to your measuring devices. They were trying to rescue the hypothesis of the stationary ether. Now, we happen to know that physical materials can't just physically contract. That's not how they behave. They never behave that way. What we would later learn, not just a few years later, is that light, in fact, does not need a medium after all through which to propagate. It is a self-driven wave, a combination of an electrical wave and a magnetic wave. It was an astonishing revelation of the day. No ether. And what state of mind, though, allows us to recognize that the speed of light remains constant? Albert Einstein to the rescue. 1905, special theory of relativity. What he noticed was that those equations that would shrink your physical objects that are doing the measurements to conspire to give you the same speed of light, what Einstein showed is, no, they don't actually shrink. What happens is the speed of light is actually constant. It's actually constant. And what's going on is that the rules of special relativity change how you end up making that measurement while you're doing it. And when that comes about, you find that the ether is not necessary, the speed of light is constant, and we have walked through a proscenium in the history of science where the ether was the last grasp, the last bastion of classical physics before the 20th century would open its doors. Because in the 20th century, what we came to learn is that whatever was your common sense that you were invoking about how the world must be,